hair and test tubes and boiling things. But no, we're going to be able to do everything in this course using the virtual environment, which is precisely what computers were made for. Now, don't worry, I'm going to help you build this lab step by step, but it will be your lab. And hold on, before you get out your calculator, all these lab environments are going to cost you nothing, just your time and patience. So let's first have a look at the requirements. When you prepare for your lab, you should make sure that your setup will meet the system requirements. Because we're going to get into using virtual machines as well as some other processor consumer tools, I highly recommend that your system is capable of handling at least 2 virtual machines simultaneously. Now, for storage. I'm not going to throw out some random numbers about the size of available hard drive space, but you really will need some. Now, if you don't have enough, you're probably going to face some problems. Now, what about memory? You don't want to have any insufficient memory fail, so I strongly advise using at least 16 gigabytes of RAM. Now, for your processor, I think if you try this course, it means to me that you probably have a processor that will support virtualization. Now, you should activate it from BIOS if this is the first time for you using a virtual machine. Now, what about for a hypervisor? Well, VMware Player, VMware Workstation, or VirtualBox, all of them are good options to build the lab on. However, what you're going to see me do is use VMware Workstation Player, because some intentionally vulnerable virtual machines work only on VMware Workstation Player. I'm just saying. And then finally, internet access. Of course, you're going to need the internet, but only when you're setting up the lab. Otherwise, I don't think you're going to need it, but it's going to be good to be able to search for extra information, so I'll leave that up to you. Now, again, before diving into the building process, I do want to show you the overview of what our lab is going to look like, and the basic idea here is to create a server that has some vulnerable web applications. Therefore, we can attack these applications from Kali Linux, which will be our attacking machine. Also, of course, we're going to need a web server to host the vulnerable web applications. So when you complete the lab with me, you will have a Kali Linux virtual machine with internet access. So when you complete the lab, you will have a Linux server as well. Now, in my case, the IP address of Kali will be 192.168.204.128. And a vulnerable server will have the address of 192.168.204.130. So these addresses may be different in your environment, but I trust you know IP addresses and subnets to know the difference. Then, of course, these machines must be able to communicate with each other. So generally, a real-life network system contains hosts, servers, routers, switches, firewalls, and, well, sometimes many other components. So you're going to need to divide the network, do some cabling, and configure the components as well. However, that's not all. And I might even go so far as to say that may be the very least. So in other words, you're still going to need to do more, both with the physical components as well as software. But what should you do when you need to try to simulate a network? Now, as an individual, you can, of course, pay for all the network components and equipment. But I don't think that's going to work here. So, thanks to virtualization technology, that's going to help us build our own network system. So, I think virtualization is a great place to start. Although I'll tell you this, that containerization technology, that's coming up in the field these days, but you're going to want to start by learning virtualization. VMware Workstation Player. So, with virtualization software, you can create a fully functional real-life network inside your host computer. Virtualization software is very powerful, and they also have a rich set of features that compare to dual booting machines. They mostly support cloning a virtual machine, and you can duplicate a VM as well. And again, most of them provide taking snapshots of the VM so that you can revert back to a clean state just in case you mess up your machine. So this feature, Revert Back, is terrific. And you'll certainly understand what I mean if you can't visualize it yourself when we practice. Now, another great feature is the ability to be able to change the size of the virtual disk, the RAM, number of processors, and so on. Now, naturally, you're also going to find the networking options and virtualization software are impressive. Generally, they have a different perspective for networking. Host-only, NAT, and bridged are only some of the options. So at the very beginning, that might confuse you, but don't worry, because in the demo section, I'm going to show you how you can choose and configure these options. Now, you're also going to be allowed to enable some additional features, such as copying and pasting text between the host and the virtual machine, as well as improved graphic performance and synchronization of the clock. Now, of course, along with these features, there are some drawbacks when you need to run a process-intensive task, such as cracking passwords. What? We get to crack passwords? Remember, this is ethical hacking, but we don't need to use that much processing power in the lab itself. So anyway, in this course, you can use VMware Workstation Player as a desktop virtualization application. So it is a virtualization software package for 64-bit computers running Microsoft Windows or Linux. It's available for free for personal use, and it's supplied by VMware Inc. Now, VMware Player can run existing virtual machines as well as create its own. It uses the same virtualization core as VMware Workstation. So VMware Inc. does not formally support the player, but there is an active community website for discussing and resolving issues. Now, I think that its power lies in the fact that it's deceptively simple to use. But I don't have the intention to tell you everything about it. You really should familiarize yourself with all the features that certainly I tell you about virtualization software and anything else that you've either gathered before or can research on your own. But for now and for this course, let's go ahead and install it, and then we can have a quick look at the tool. So, open up your favorite browser and type VMware Workstation Player in the search box. And click the first link to go to the download page. And you can see the latest version here is version 15, so we're going to use this version. And if you scroll down a little bit, you'll see the download options for the major host systems. Click on the option which is suitable for you. So, of course, what I mean by the host is what your main operating system installed is on your computer. Now, here I'm using Windows 10 as my host, so I'm going to download the Windows option. But you can instead download for Linux if you are indeed using the Linux operating system. So, okay, let's save the file, and the download has started. Now go to your Downloads folder, and let me just close the browser, and double-click on the exe file, and the installation will start in a few seconds. Now, the installation process, of course, is very easy. Just click Next. Okay, read the license. Please, as you always do, I'm sure. Then accept the license agreement. Click Next again. And I don't want to install this feature, so I'm going to leave it unchecked and click Next. Good. Now, also, I'm going to uncheck these fields and click Next again. Next. And now I can finally click Install. Now, it's not going to take that much time to install, just a few seconds. And there it is, the installation has finished. Now, you can also provide a license if you have one, but we're not going to need a license. We're just going to use it for personal use only, and click Finish. All right, so now you're done, and I'm going to close this window, and then here on my desktop, there's a shortcut for the Workstation Player. So I'm just going to open Workstation Player by double-clicking on it. And like I said earlier, the first option is good for us. Click Continue. Alrighty then, so this is the Workstation Player window. There it is, in all its glory. That's what it looks like. Very simple, yet very powerful. So at this point, I'll offer congratulations because you have installed VMware Workstation Player. I want you to play around, be familiar with some of the menus before you start hacking, okay? So right now, let's install some of the other components for your lab. VirtualBox is a freely available open source software solution, runs on Windows, Linux, Macintosh, and Solaris hosts, and supports many guest operating systems. So VirtualBox is deceptively simple, but it's also very powerful. So let's go ahead and install it, give it a quick look. Hey there, so I want to make a particular hands-on demonstration in Windows for two particular reasons. One, I'd like to show you that the host is not critically important while preparing the lab. And secondly, I'd like the students using Windows as a host system to feel comfortable at the beginning of the course, because we're going to be using a Mac as a host system in general for the rest of the course. So simply by using your favorite web browser, type VirtualBox into the address bar. You will see the official site of VirtualBox is the first row of the results page. So it's virtualbox.org is the official site. So click on it. And on the left pane, there's the download menu item. So let's click it to see the download options. All right, so this is the latest edition when I was preparing the course. Now, there's a couple of options for the major hosts. So, by the way, what I mean about the host is that your main operating system installed on your computer. So click on the option, whichever is suitable for you. Right now, I'll use a Windows 10 machine as the host. So I'm going to download for Windows hosts. And while downloading VirtualBox, just scroll your mouse down a little bit and you can see that there's an extension pack to install as well. The extension pack helps your installation support different things like USB 2 and 3 devices. It's not an obligation, but it may help you to manage your installation easily. Now click on the link, All Supported Platforms. Wait a little bit. It might not take too much time. All of it has been downloaded. Go to my Downloads folder. Double-click on the X file. Click Next, Next, Next. And now it will install some virtual network adapters at this phase. So click Yes and Install. Now it's going to be installing for a while. And there it is finished. I don't want you to start now, so let's uncheck the box and click Finish. See, now's the time for installing an extension. After installation of VirtualBox, the icon has changed. You see that? So double-click on it and wait for a bit. Right, so now this screen comes up. Click Install. So go ahead and scroll down until the end, and you'll see that I agree button. It's enabled. So click on it if you agree, and, well, you should agree in order to use VirtualBox. So wait a second. Okay. So now you're done. Congratulations, you've installed VirtualBox. So please have a look and be familiar with the menus by yourself before you start. Virtualbox.org is the official site. And on the left pane, there's the Download menu item. So in the Downloads page, we have platform packages here. Click on OS X Hosts as a link for Mac devices. Now select the appropriate location for the installation package and click Save to start the download. When the download's finished, double-click on the installation package file, which has the .dmg at the end. Okay, so here you do what the instructions tell you. Double-click on the VirtualBox.package icon, click Continue, continue again, and Install. And then here I just enter the local admin password and click the Install Software button. Now, go to the Applications menu and click the VirtualBox icon to start your virtualization environment. Congratulations, you've installed VirtualBox. Now I want to show you how to install Kali from the ISO file. The first step is the same, downloading the installation file. Here, the ISO file. Open the browser and simply Google the words Kali and download. The first website is the official site of Kali, so click on it. This is the download page of Kali. And these are the ISO files. You can use them to install Kali as a main host or as a virtual machine in any virtualization platform. Now, there are 64-bit and 32-bit versions, as well as new image styles of Kali Linux, Installer, Live, and Net Installer. At the bottom of the Kali image files table, there are ready-to-use, well, almost ready-to-use Kali virtual machines. So if you do want to use Kali as a virtual machine, you can use them instead of installing ISO files from scratch. So I'd like to download and install the ISO file of the 64-bit installer image of Kali. So I'll just click on this link to download the ISO file via the protocol that we affectionately know as HTTP. And now we can save the file and have a look at that. So what do you think the second step of installing Kali from the ISO file is? That's right, installation. The ISO file for Light Kali has been downloaded and it's in the Downloads folder. Now I go to VMware Fusion Virtual Machine Library. From the upper left corner, click the Add button and select New. We're on the installation method selection window. So the big option, which is selected by default, is our option, install from disk or image. Now I can click Continue to move on. So now is the time to select the ISO file. We can't just drop the file if we drag it from over here. Here's the file browser. Select the ISO file, drag and drop it in the installation wizard, and click Continue. In the next step, we have to choose the operating system of the VM. Now we know that Kali is a Debian-based Linux distro, and we downloaded the 64-bit version, so choose Linux, then the 64-bit version of the latest Debian, and once again click Continue. You can select the firmware type of a virtual machine. Legacy BIOS is a standard BIOS firmware. UEFI is an interface between the operating system and the platform firmware. So if you do select UEFI, you have the option of enabling UEFI Secure Boot. And of course that secures the boot process. So now here I'm going to choose the Legacy BIOS option. So now we're on the last step of installation, and there's a summary here. The default values are 2 gigabytes of RAM, networking, etc. So when I click the Finish button, it asks for the location and the name of the VM file. I'm okay with the default. It's better to collect VMs in the same location, in my opinion. That way I stay organized, and I recommend you do too. And click Save. Now the VM boots for the very first time. In the boot menu, choose one of the install or graphical install options. I'll show you what the graphical install looks like now. Now, as you see, it's a typical operating system installation. We need to configure the OS now. So I'll select the language, location, and keyboard configuration. And now network configuration has been completed successfully. So I'll set the host name to Kali. And let's give it a domain name. I'll just choose the same name and continue. I'll set the username and password for the new user. Because Kali will not use a root account by default when it's started. Don't need any partitions. We're only installing Kali Lite as a virtual machine, so it can use the entire disk reserved for itself. Continue. Keep going with the default options for disk partitioning. Yes, write the changes to disks. Now the system is being installed. And just like before, it may take several minutes. So here Kali asks for the HTTP proxy information, but we're not going to need it now, so we can just leave it blank and continue. And in this section, you can choose the desktop environment that you want to use. Kali is no longer offering separate images for every desktop environment. There's just a single image for all of them. And it can be chosen during installation. So I will continue with the default option, XFCE. It's asking to install the grep bootloader to the master boot record. Now, this is more meaningful when you install an operating system as a second one on the host. We're just installing a virtual machine, so it's the only operating system for it. So, yes, install the grep bootloader to the master boot record. We have only one partition to install grub, so I select that and continue. And installation is complete. So, it's time to boot into our new system. Continue. We are finally at the login screen. Log in with username and password that you've set. Welcome to 64-bit Kali installed by the ISO file. So I want to turn it off for now. Now let's go to the folder that we chose for installation. Order by date modified, and here is the Kali Lite VM file. So now is the final step. Run the VM and fix any problems. So we installed the Kali Linux 64-bit installer image VM in the previous lecture. Now, let's boot it and just make sure everything's okay. I know it will be, don't you? Okay, so we'll log in with the username and password that you set during the installation. And welcome back. All right, so let's take a quick look at the menu of the default XFCE desktop environment. And it is here in the upper left-hand corner, and these are the default tools of Kali. So first of all, let's open up a terminal screen and switch the user to the root account. And then this way we don't have to write the sudo command every time. And look at the IP address assigned by the VM. So let's ping a remote system, for example, a Google DNS 8.8.8.8 to check the internet connection. We receive the packets, no packet loss, and we have internet connection now. So just to double check, I open the web browser and visit any website on the internet. And it's okay now. If you are having problems with an internet connection, just check the solutions mentioned, Kali from VMware image, step 3, and that should help you fix the problem. Now, what about the local area network? Can the Kali 64-bit VM see the other systems in the same network? So I'll ping the Kali VMware machine, the IP 222. And here are the packets, so everything's okay. And that means we're ready to hack. Again, to double check, I'll go to the Kali VMware machine and ping the Kali 64-bit. Now, what was the IP of the Kali 64-bit machine? Here, it's 133. Okay, so now I'll just go to the Kali VMware machine and ping 133. And sure enough, everything is okay. I love it when everybody talks to each other error-free. So, Kali Linux is a Debian-based Linux distribution aimed at advanced penetration testing and security auditing. Kali contains several hundred tools which are geared towards various information security tasks, such as penetration testing, security research, computer forensics, and reverse engineering. Kali Linux is developed, funded, and maintained by Offensive Security, a leading information security training company. Now, we're going to use Kali as the attacker system. However, if you don't want to use Kali for whatever reason, you can download the tools that we use and install them to your host machine. So let's download it and install it as a virtual machine on our host system. So I'm going to prepare the Kali VM directly from the VirtualBox image first. The first step is to download the VM files. Open the browser and simply Google the words Kali and download. The first website is the official site of Kali, so click on it. This is the download page of Kali. These are the ISO files. You can use them to install Kali as the main host or as a virtual machine in any virtualization platform. Now, these are the images that you can use to install. With the latest release, Kali Linux announced that the images have been restructured and simplified. So from now on, Kali Linux has new image styles: installer image, a live image, and a network installer image. Installer image is recommended for users who want to use Kali Linux on their system. No network connection is required. You can choose desktop environments such as XFCE, KDE, GNOME, and any other tools that you want to install during your installation. Now, the second one is a live image, so it's used to run Kali without installing it. And the last one is a network install image. The smallest image, of course, to download, containing only enough to install the base system that requires a network connection to install selected applications. At the bottom of the Kali image files table, there are ready-to-use, almost ready-to-use Kali virtual machines. So if you're going to use Kali as a virtual machine, you can use them instead of installing ISO files from scratch. I'm just going to use one of these images now, so I'll click on this link. So now we're in the Virtual Images page. Scroll down a bit, and here are the images. Click this link under the Kali Linux VirtualBox tab to download the OVA file. And the download has been completed. So here you can just simply run the OVA file to run the VM. So the second step is to install Kali. Well, since we'll use the OVA file, it'd be better to say import for this step. And the download's finished. It's under the download folder. Now I'll open a VirtualBox interface, choose import, and choose the OVA file under the download folder and click continue. So as you can see, there are the suggested settings of VirtualBox for the imported virtual machine. RAM is 2 gigs by default. Now just click Import and agree to the license agreement in order to continue. And it starts to import. It may take a couple of minutes. So I want to look at the size of the empty space on my host. df command simply displays the free disk space, and -h parameter makes the result human readable. Now I have 140 gigabytes of free space, and that should be plenty for this installation. Installation's finished, and this is the summary of the VM. RAM is 2 gigabytes by default, and if you have enough RAM on your host system, I suggest you increase it. Networking is NAT, just as I want. Now just click on the Start button. Okay, the virtual machine could not be started. So I wonder about the details of this error, don't you? Okay then, so to fix this problem, we'll need to install the Oracle VM VirtualBox extension pack. So I'll copy this part, and I'll just search on the web. So now let's look at the official site of VirtualBox. We can download it under the title of Oracle VM VirtualBox extension pack. So we'll just click on this link and save the file. And it quickly downloads. So let's open the file and click Install. And again, I'll accept the virtual license agreement. And finally, enter the password to complete the installation. And now it's been installed successfully. So now I'd like to go to the Preferences and double-check the extension packages. And everything is okay. Good. So now we can start again. Okay, so our Kali is booting for the first time. Click Switch for the full screen mode. And here we are at the login screen. Now, in addition to the changes that I mentioned in the previous lecture, there is another important change in this Kali 2020.2 release. The default user account is now a standard unprivileged user. Kali is no longer using the super user account root by default, right? So the new default credentials are Kali and Kali. And welcome to Kali 2020.2. Now, normally the screen resolution automatically fits your particular screen, but if you have any resolution problems like I appear to be having, you can change the scale for your screen. So first, I'll just open up the display settings, and I can choose the resolution value to be 1920 by 1200 and click the Apply button. Now go to Preferences, and under the Display tab, you can change the scale factor. So I'll set this value to be 190% of my screen, and you can change it to whatever you want and just try different values for your screen. All right, so I'll click OK. Now let's look at the changes. Yeah, that's pretty good. So let's open a terminal screen and check the network connection. When I run the ifconfig command with standard user privileges, I will get an error because the ifconfig command is under the sbin folder and requires root privileges. So why don't we have a look inside that sbin folder? As you can see, I can run the cd, pwd, and ls commands without sudo. These commands do not require root privileges. However, the commands that are under the sbin folder must be run with sudo. Ifconfig is here, and let's run this command with sudo. And it's okay now. Of course, there is a more practical solution. We can always switch the user to root so that we don't have to write sudo for every command that requires root privileges. So let's run sudo su. Okay, so I'm root now, and I'll double check that with the whoami command. Well, now I can run any command which requires super user privileges without sudo. And this is my IP address. If ifconfig didn't obtain an IP address, that means that you have a problem with your network configuration. It's not a problem. Problems do occur, and I certainly will give you some solutions to fix any possible network problems in the next lecture. So now we're on the last step. Fix the problems and run Kali. Now in this lecture, I will assume that you do have trouble with network connections, and I'm going to give you some solutions so that you can fix the problem. Now, hopefully you're not facing such a problem, so if you don't have a network situation, please, you don't have to apply any of these solutions in this lesson, but it's good to have you on the ride, and you can always sharpen your troubleshooting skills. So first off, let's reboot the machine to understand whether the problem is an exception for the initial run or not. So I shut down the virtual machine because I want to look at the settings of it. Now select Kali and click the Settings button and click the System tab. I want to make the RAM 3 gigabytes. So now I can click the Start button to boot it again. Username and password are both Kali. Okay, we are in again. So let's check the network connection by clicking the network icon at the upper right-hand corner So I think there's a problem on the DHCP of the VM. Well, anyway, we can live without DHCP as well. So I'm looking at the wired network. Don't be confused, even though you share the wireless connection of your host machine, it's simulated as a wired network in the VM. So let's open a terminal screen and look at the networking service if it's running. Write Service Networking and press Tab twice to see the available commands of the service. Networking service does not have status command, so I'll assume that it's not started and try to start it. And if you are still not connected at this point, let's go to Network Settings. You can go to Network Settings via Advanced Network Settings under the menu. Or you can right-click on the network icon in the upper right corner and select Edit Connections. Now click the wheel icon under the Wire tab, okay? I go to the IPv4 tab to set the IP manually. Click the Manual option. I'll choose an IP for the new collie. Now the IP block of my virtual network is 10.0.2.0 through 24, so I'll choose an IP from this block. Netmask is 255.255.255.0 for a 24 IP block. The gateway is 10.0.2.2, so I can use Google DNS as my DNS server and route. Now you can click the Save button. Okay, I'll reboot the machine to be sure that the changes are applied. Boot completed. So open the terminal screen and first type sudo su to switch the user to root so that you don't have to write sudo for every command that requires root privileges. And then run the ifconfig command to see the IP address of Kali. And it's 200. So let's ping a remote system, for example, Google DNS 8.8.8.8. Yes, we received the response packages. The network's okay now. So to double check, open a browser and visit any website. Metasploitable download and install. So let me describe a little bit to you. Metasploitable is a virtual machine image that is created by SoundForge. Now, this is a virtual machine where there are many vulnerabilities, so that's why it's fun to play around with. Metasploitable, to be clear, is a deliberately vulnerable Linux virtual machine. So this VM can be used to provide security training and test security tools, as well as practicing for common penetration testing techniques. What a coincidence! Now, to install Metasploitable, you'll first need to download the disk image file to the computer. So for this, we can open up the favorite web browser and type in Metasploitable into your search engine. And from all these results, just click on the link that is going to SourceForge and click Download on this screen. And just by clicking the Save button on the incoming screen, it'll start to download the image file to your computer. And of course, depending upon your internet connection speed, the download process could take some time. Metasploitable Virtual Machine Installation. So now we're going to install Metasploitable Virtual Machine using the Metasploitable image file that we downloaded. So we will show this image file as a disk to VirtualBox virtualization software. So why don't we start? Open the Downloads folder and extract the Metasploitable Linux 2.0 file from your Downloads folder, wherever you put it. So now let's copy the Metasploitable 2 Linux folder and paste it into the Metasploitable 2 Linux folder on your C drive users username VirtualBox VMS folder. Paste it there. Open Oracle VirtualBox and click the New button on the main screen. So on this screen, we're going to install Metasploitable as our machine. So write the name that we will use for this virtual machine. In the machine folder section, let's select the Metasploitable 2 Linux folder that we copied and pasted. So in the type section, just click on Linux for Metasploitable. For version, select the type, Debian 64-bit. Click Next. So on this screen, we can determine the amount of RAM that we're going to give our virtual machine. And this value can be changed after installation, but right now, let's just set it to 1024. Click Next. And on the screen, we can specify the disk system of the virtual machine and show the location of the Metasploitable disk image that we downloaded. And click Add. So now find the Metasploitable2 Linux folder. Click on the Metasploitable.vmdk file. Click Choose. And click the Create button. And just like that, the virtual machine is created. Click Start. And the virtual computer will open automatically and comes up with username and password screen. So, username, MSF admin, and password, MSF admin. Great job. Very cool. So this is the last phase of creating Metasploitable 3. So you'll download the files and use Vagrant to build the machine from the ground up. So let's open the post about Metasploitable 3 again. Now, because you've already installed the VirtualBox, you can skip over this step. So click here to go to the Metasploitable 3 page on GitHub. And here's the page for it. You can find everything about Metasploitable 3 in here as well. So first, I'm going to download these files to start creating our virtual machine. Click this green button. Now, if you so happen to have a GitHub desktop, you can clone it. But I don't have one, so I'm going to download it as a zip file. It's not going to take long. Oh, yeah, I forgot to mention I've downloaded it before, so I'm going to cancel out of it here, but you go ahead and finish yours. Then I'll go to my Tools folder. Now, you can right-click on the Metasploitable 3 archive and extract it anywhere you want to. I'm going to extract it at my desktop. Okay, great. So extraction is completed. Now, open the file that you extracted the files to, and you will see a PowerShell script named build.ps1 in that folder. Yeah, you can have a look at it if you want. And as you can see here, it looks like default installation directories. Now, if it doesn't find it, it will try to install the suitable version all by itself. So pretty much the script will build everything for us. Well, almost everything. Yeah, from the start, open the PowerShell command terminal. Now, change your directory to the main Metasploitable 3 directory that you have extracted the files to. Now, I'm going to list files to show you and type /build.ps1 Windows 2008 to build Windows version of Metasploitable 3. Oh, let's forget to change my execution policy. And I'll right-click on the PowerShell icon on the taskbar to run PowerShell as an administrator. So I'm going to change directory immediately. And by the command set execution policy unrestricted, I will not get this error anymore. So type Y to this question. Alrighty then, the build has begun. Now, this is going to take a while, I assure you. So go and have a few cups of coffee and bake your friends a whole bunch of bread and rolls and anything else you can find. But in the meantime, Vagrant is going to make a lot of things for you. Now, you do have to wait and be patient and not interrupt the process. So I'm going to pause the recording here, and I'll come back when it's done. All right, so Vagrant did a whole lot of things. Now, you should do one more thing to stand the virtual machine as a VirtualBox file. So I'll open a new administrator PowerShell for myself and type Vagrant up win2k8. So this command is going to help Vagrant to install some other things and make the virtual machine ready to use. And it's going to take some time again, so, wow, maybe it's time for another cup of coffee. So now you're going to see many lines on your PowerShell screen. However, on my screen you won't see as many because, well, this is my second attempt to use it. Okay, so it's finished. So when you open your VirtualBox, you will see Metasploitable 3 there. So choose Metasploitable 3 and start it up. Okay, so I recorded this error so that you can see it's not such a big deal. Right now, you should just stop the Vagrant process to free the resource. Now you can open up the PowerShell window again and type Vagrant status. Right, so as you see, the Vagrant process is running on resources of Metasploitable 3. So type Vagrant halt Win2K8 to stop Vagrant. And now it's finished. So now you can open Metasploitable 3 from the VirtualBox. And finally, you get to the Windows login screen. Now, from the above menu, click the Input, Keyboard, Insert Control-Alt-Delete. Now click Vagrant User, and the password for Vagrant User is Vagrant. Wait a few seconds. All right, congratulations. You deserve a cup of coffee. You have successfully installed the Metasploitable 3. And now you can start the course. Free Windows operating systems install. So another virtual machine that we will be using in Nmap will be Windows 7. Now, because Windows operating system is probably the most widely used operating system in the world, finding vulnerabilities related to this operating system is very important for system security experts and pen testers and, okay, I'll say it, attackers. So just open up your favorite web browser and click the Windows link on the screen to download Windows Virtual Machine, ie8.win7.virtualbox. You see that? So select that as the virtual machine in the incoming screen. Select VirtualBox as the platform. And now just click Download Zip. And the download process will probably start automatically for you. And of course, it may take some time depending upon your internet speed. And after the download is finished, you'll be able to extract the file by finding it in your Downloads folder. Now, in the ie8.win7.virtualbox folder, double-click the ie8 OVA file, and this screen will show you the features of the virtual machine to be installed. Just click the Import button, and the image file will be installed in the computer. And this process may take some time, depending upon the host computer. Okay, so after it imports that, the virtual machine that is installed will be on the left side. See it in the VirtualBox main screen, so click Start. Now, if an error message appears, that means we need to edit the properties of the Windows 7 virtual computer. The reason for the error message on the screen is that the resources of the image file won't be able to be met by the host machine. So that's easy. So in this case, we'll just make a few changes to the virtual computer. So again, we'll click on Settings. Click on the left-hand side, the system, and the RAM value. We'll set that on the right-hand side of the motherboard. And the CPU number is set in the processor. And display card RAM value set in display. NAT is the network that we will select in network section. Click USB 1.1 OHCI controller, click OK, and click on the Start button. Vulnerable virtual machine. All right, so practicing your skills always helps you in your career and your personal life, but here we're just going to stick with your professional life, right? So, there are many ways for you to gain the knowledge of web application penetration testing. You can read blogs, and you watch courses, and you participate, you watch videos, and so on and so forth, but nothing will ever beat actual hands-on experience in order to improve your skills. Hands-on experience allows you to understand the procedures and methods of securing web apps. So you're going to get your hands dirty to get more out of this course. And it's a good thing, because you know what? Muscle memory. That's all I'm going to say. Now, to accomplish everything that we've been talking about, you must have a vulnerable web application so that we can try to build that lab, right? Of course, you can develop a web app by yourself, but it's not necessarily reasonable when you're new to web vulnerabilities. So you must first exploit and learn what the vulnerabilities of web applications might be and what they look like. So as web penetration testers, it's vital to be aware of real-world applications, which are very diverse in many, many ways. They're built with various technologies, and each of them can be served up differently. So, to be prepared for testing, we should practice and improve our skills. Stands to reason, right? Now, thanks to our security community, we can find many intentionally vulnerable web applications on which to practice. So that means that we can download these applications' source code and then use them in our environment. Also, there are some pre-built virtual machines that contain these applications already. And by using these virtual machines and applications, that way you ensure that you have a safe environment in which to work. Beatbox. Now, I didn't say beatbox, although that would be fun. But I just want to let you know that you can develop your attacking skills, identify and exploit vulnerabilities in web applications with this. This is an OWASP project called Vulnerable App Directory Project. And it holds and categorizes pretty much almost everything for us. Most of the vulnerable applications can be found in this project. Now, here are many options when you need vulnerable applications in virtual machines. Now, thanks to the community for this purpose, many buggy apps are developed. So that means it's intentional. You can find and review a list of all known vulnerable web applications here. And if you're not necessarily comfortable using an already built configuration, of course, you can create your own vulnerable system from the very beginning. Some developers, that's what they do without even knowing it. I'm just kidding. All right, so I need to be honest with you. When I was first planning out this course, I was planning to create a vulnerable machine from the very beginning by myself and have you do it as well. As I've said, I really do believe that this has many benefits in order to learn application deployment process at the very least. But as I already told you, what I decided was it's too time-consuming and it certainly isn't for beginners. So, for that reason and others, we're not going to do it that way. In this course, we're going to use a prepared virtual machine called Bbox. Okay, so Bbox contains the buggy application BWAP. Buggy Web Application, in case you're wondering. Therefore, we are going to play with the BWAP in this course. So it's based on PHP, and it runs on the MySQL database server at the back end. It has 3 levels of security, low, medium, and high, and each level demands different skills. So it covers all risks from the OWASP Top 10 project, with all major known web vulnerabilities, such as XSS, CSRF, SQL injection, file injection, upload flaws, and many more. So at any time, you can easily reset the database if you figure that you want to start over again. And it comes with a simple, straightforward interface. Alas, don't let that deceive you, because it's only for learning purposes. Now, another great feature, you can also view the vulnerability in the source code. So it means that you don't really need to try something blindly like a script kiddie. You can observe and measure what you're doing by looking at the source code. Okay, anyway, let's just install this box into the lab. So open up your favorite browser, and this time type BWAP, and follow the first link from the results of the search. And here we are at the official website of the owner of the application. And now we can go to the download page. Click the link below to download Bbox, and you will be redirected to sourceforge.net. So click here to download and save the file. Download will take a few minutes, and this time I am absolutely sure that I'm not going to record the entire download process. Okay, so after the download finishes, go to your download folder. And what do you know? Here is the downloaded file in 7-zip format again. So let me just close the browser so that you can have a clean view. Okay, so right-click on the file, extract the files. Now I'm going to extract it to a new folder under the previous folder that I created for virtual machines at the beginning of the course. And I'll wait a few seconds until the extraction finishes. All right, so the extraction is done. Let's go to the folder. And here are the files. And double-click on the file with this VMX extension. And now the virtual machine will start in full screen automatically. And again, we're going to come up against this warning. And just click on I moved it and continue. Okay, so now in a few seconds, the B box will start. And here is the desktop environment of our virtual machine. And I'm going to offer congratulations yet again. You have imported a vulnerable machine into your lab environment. Good job. All right, so now we have imported the pre-installed BWAP virtual machine. It's also possible to download the application code itself and use it, but we're not going to do it that way. So one thing to keep in mind, these kinds of applications are, they're damn vulnerable. Don't upload them to an internet-facing server. They will be compromised. So believe me, I did it once for experimental purposes, and it did not take any time at all for it to be hacked. Now, in case you think I'm giving you permission to do that, again, just make sure that you set it up in a secure environment. VirtualBox network settings. So let's set up our virtual network. It is, of course, required to use VirtualBox because we really do want to avoid accidental damage to actual systems during this course. So, therefore, we will ensure that all virtual machines that we are going to be using will be on the same virtual network. So the network is the ability of multiple devices to communicate with each other. You know that, right? It's either going to be wired or wireless. And we can use this to connect a network device, typically. So we will configure the NAT network so that all virtual machines that we're going to be using are on the same network. Now, when we create a NAT network, Oracle VirtualBox will be the program that will automatically assign an IP to all the computers in this network. The IP, of course, is the address that is required for a computer to communicate with other computers over this network. And each computer has to have its own or different IP. In fact, each computer connected to the internet has a different IP address. The IP refers to the address for computers. The address of each computer has got to be different. The IP address is available in two different versions, IPv4 and IPv6. Now, widely used across the world is IPv4. It's 32 bits, and it consists of 4 8-bit numbers, each separated by dots. So here's an example, 192.168.1.1. Now, each number group can have a value between 0 and 255. So if there are two computers with the same IP, there will be IP conflicts in the network. So in order to prevent this, DHCP, or Dynamic Host Configuration Protocol, is used. And what DHCP does is assign a different IP to each computer. So therefore, you don't have an IP conflict, right? So NAT establishes the network. So we'll click File, click Preferences, and click on Network. And now click Add New Network on this screen, and click on the arrow, and then Exit. Now the virtual machines will need to get into this NAT network. So click Virtual Machine, and click Settings, and click on Network on the incoming screen. So on this screen, select NAT Network from Attached To, and click on the arrow. And then you can follow the same process for your other virtual computers. Connections test. Great, so now we're going to test whether the virtual machines installed will be able to see each other. So for this test, we'll be checking to see whether each virtual computer can communicate with the other virtual computers on the network. Now, for this purpose here, this test, it's enough to just check whether the virtual computers are on the same network and therefore then can ping each other. So we can check the network settings, or you can check them with a command line in order to check the IP value. So for me, I use a CLI because many programs used for penetration testing run through the command line. The command line command is an important advantage, and you know what? You'll get used to it because not all programs have GUI screens. So let's check the IP value from the command line. Now, of course, different operating systems have different ways, whether it's Windows, Linux, or Mac OS. For IP control on Linux and Mac OS, open up the terminal, write ifconfig on the command line, press enter, and then on the incoming screen, you can see the computer IP. IP control for Windows computers. Open the command line, click Start, and write in cmd, click cmd.exe, open the command line, write ipconfig in the command line, and press enter. And you can see here that we have the computer IP on this incoming screen. So now open VirtualBox. Click on the Kali Linux virtual machine on the left-hand side of the VirtualBox screen. And click Start from above. And then after opening Kali Linux, you can log in by entering the username and password. Now click Terminal on the desktop. Open Terminal and check IP information. Just type ifconfig. Great, so once Metasploitable opens, you can put in the username and password. And on the incoming screen, write and check the information by typing ifconfig. Click on the Ubuntu virtual machine on the left-hand side of the VirtualBox screen, and after Ubuntu opens, you can log in by entering the username and password. Now click Show Applications, search Run Terminal, press Enter, and when the terminal opens, you can check the IP information by typing ifconfig. Now click on the Win7 virtual machine on the left-hand side of VirtualBox, and click Start from above. And then after Windows 7 opens, you can enter the username and password, and click the Start button. Write CMD in the search bar, enter, and the command line opens. So now you can type ipconfig on the command line, and then you can check the IP information. Okay, so now we need to test that the Kali Linux virtual system can communicate with the other virtual systems over the network. So open up Kali Linux for this. Click Terminal. Now we need to ping the IP address of the Metasploitable computer. So to do this, enter ping 10.0.2.4 and press Enter. And the display will show that the ping packets are gone. So in this case, communication is taking place. Ping the IP address of the Ubuntu computer, and just enter ping 10.0.2.7 and press Enter. And the ping packets are gone. So in this case, again, communication is taking place. So now we'll ping the address of the Windows 7 computer, enter ping 10 10.0.2.5, press enter. Now look at the display. The ping packets did not leave here because the ping requests are blocked on the firewall of a Windows 7 computer. So that means that in this case, we need to employ reverse communication. So just enter Windows 7 and click the Start button. And in the search field, just enter command. Command line opens. Now here, just enter the IP address of the Kali Linux computer. So that means enter ping 10.0.2.5 and press enter. Okay, so now we see that the ping packets are gone. So in this case, we know that our communication is working. So in this lesson, we are going to learn common bash script commands. Okay, the bash script is one of the most popular programming tools available in Unix. Bash is an extremely powerful and useful part of developing scripts. It can fit repetitive tasks into a single line of function calls. Thus, many long commands can be reduced into a single executable command. Doesn't that make life easy? So in this tutorial, we want to show you the 15 most important and pretty common commands that are used in bash scripting. The first is ls. So the ls command, it'll allow you to quickly view all the files within the specified directory. Second one is echo. The echo command prints text to the terminal window and is typically used in shell scripts, as well as batch files to output status text to the screen or a computer file. The third is grep. So the grep command is used to search the text for patterns specified by the user. It's really one of the most useful and powerful commands out there. The fourth is pwd, and the pwd command is used to print the current directory that you are in. For example, if you have multiple terminals going and you need to remember the exact directory you're working in, then pwd is going to tell you. The fifth is cd. So cd will change your current directory. Some people confuse it with change directory, and no. Remember current directory. Anyway. The sixth is redirect, std out. So the greater than character is the redirect operator. So it takes the output from the preceding command that you'd normally see in the terminal and sends it to a file that you give it. The seventh is sleep. The sleep command will delay a process for a specified amount of time. The eighth is cat. The cat command is one of the more versatile commands and serves three main functions: displaying them, combining copies of them, and creating new ones. The ninth is read. The read command is a bash built-in command that reads the contents of a line into a variable. The 10th is exit. The exit command will close a terminal window, end the execution of a shell script, or log you out of an SSH remote access session. The 11th is clear. So this command is used to clear all previous commands and the output from the consoles and terminal windows. The 12th is chmod. The chmod command gives permission to upload, delete, run, or change a file. The 13th is kill. The kill command allows you to terminate a process from the command line. The 14th is CP. The CP command copies files and directories, so you can use this command when you need to back up your files. The 15th is the man. The man command is your manual and is very useful when you need to figure out what a command does. For example, if you did not know what the command mkdir does, well, you could always use the man command to find out. Go ahead, check it out. Anyway, in this lesson, we learned some really useful and pretty common bash commands. Welcome to the basic concepts of penetration testing and ethical hacking section. Now, before learning how to perform penetration tests on live systems, let's first learn exactly what the penetration test is and what the basic concepts are, the way that I define them, and the way that I'm going to use them throughout the course. Please, I want to warn you that this section is prepared to teach you the basic concept of penetration testing and ethical hacking. So I strongly recommend watching the lectures of this section. However, if you already know the concept and terminologies of penetration testing, or if you're just impatient and you really want to get right to the hands-on practice, you can go ahead and skip this section. I give you permission. Not that you needed it anyway. In this section, we're going to learn what the penetration test is, and from now on, I'll just abbreviate it to pen test. The types of security tests and audits that we perform to understand the strength of an IT network, security audits, vulnerability assessments, and pen tests. The basic concepts of offensive security, asset, threat, vulnerability, and risk. The pen test approaches from black box to white box. And what about the steps of planning a pen test? What is the purpose of the test? What is the scope of the test? What are the requirements to test the scope and the restrictions of the test? We're also going to learn the main phases of a pen test. Reconnaissance, aka information gathering, scanning the network and scanning for the vulnerabilities. Exploitation, aka gaining access, and post-exploitation. Covering the tracks of the test and reporting the test results. We're also going to learn the legal issues that you should know about and obey, and the worldwide organizations that determine and publish pen test standards. So, first things first, what is the penetration test? To answer this question, I would like to show you 3 definitions from 3 different resources. Talk about reconnaissance. The first one is from Wikipedia. The definition of penetration test in Wikipedia is as follows, and I quote, "An attack on a computer system with the intention of finding security weaknesses, potentially gaining access to it, its functionality, and data." End quote. Now, I want you to pay attention to the words "with the intention of finding security weaknesses." Second definition is from the CISSP Preparation Guidebook, and I quote, "A pen test can determine how a system reacts to an attack, whether or not a system's defenses can be breached, and what information can be acquired from the system." Now, the words that I want to emphasize here are how a system reacts to an attack. And the last definition is from another book. It's called Penetration Testing, Protecting Networks and Systems. And I quote, "Pen testing is the simulation of an attack on a system, network, piece of equipment, or other facility, with the objective of proving how vulnerable that system or target would be to a real attack." End quote. I want you to notice the words here, the simulation of an attack. So my take on this, since you're asking, is basically bringing a few of these selected parts of the previous definitions together. So my definition, a penetration test or pen test is the attack simulation on IT systems with the intention of finding security weaknesses to determine how systems react to these weaknesses. See what I mean? Now, in a cybersecurity point of view, we can classify the cybersecurity tests and audits into 3 parts. A security audit, typically checklists of best practices, of course, in terms of cybersecurity. Vulnerability assessment, identifying the security holes. And penetration tests, the main subject of this course. Now, a computer security audit is a manual or systematic, measurable technical assessment of a system or application. Security audit assessments include performing security vulnerability scans for best practices, interviewing staff to understand the level of information security awareness, reviewing the access controls of the applications and operating systems, and analyzing the physical access to the systems. An important point to take into consideration is, in order to be able to get the most accurate results, we should perform the security audits with admin privileges. Now, perhaps the major question is, where can we find the best practices to perform security audits? Good question. Thankfully, there are some organizations and consortiums which regularly publish and update the security audit checklists of IT systems. And these are the most popular organizations to collect checklists from. The Center of Internet Security is a nonprofit organization formed in October of 2000. Its mission is to, quote, identify, develop, validate, promote, and sustain best practice solutions for cyber defense, and build and lead communities to enable an environment of trust in cyberspace, end quote. Now, they call checklists benchmarks, but benchmarks are not the only thing that they're known for. In fact, if you're administering IT systems, CISecurity.org should be one of your home pages. Bookmark it right now. I'll wait for you. NIST, the National Institute of Standards and Technology. It's a physical sciences laboratory as well as a non-regulatory agency of the United States Department of Commerce. Its mission is to promote innovation and industrial competitiveness. If you visit their website shown in the slide here, you'll find the National Checklist Program repository of their National Vulnerability Database program. They have a wide range of up-to-date checklists. To help system admins automatize the audits, a couple of checklist formats have been created by these organizations. If you can create your own programs or scripts according to these standards, you'll be able to use a massive number of checklists to audit your systems. I'll let you know what some of the best known checklist standards are. XCCDF. The XCCDF acronym stands for Extensible Configuration Checklist Description Format. However, as the name suggests, the language is used to describe the security checklists. The language is designed to support information interchange, document generation, organizational and situational tailoring, automated compliance testing, and compliance scoring. OVAL. The OVAL acronym stands for Open Vulnerability and Assessment Language. OVAL is declarative language for making logical assertions about the state of a system. Its main component is the SCAP standard. It's used to describe security vulnerabilities or desired configuration of systems. OVAL definitions define a secure state of some of the objects in a computer. For example, configuration files, file permissions, processes. OVAL definitions are evaluated using an interpreter called Scanner. You can, of course, create your own tool to automate your audits or use the tools created before. CISecurity has a tool. It's called SysCat, CISecurity Configuration Assessment Tool, which automates benchmarking of a number of operating systems. Vulnerability assessment is a process of defining, identifying, and classifying the security holes in IT systems. An attacker can exploit a vulnerability, the name of a particular security hole, to violate the security of a system. Now, some known vulnerability types are authentication, authorization, and input validation vulnerabilities. And the main difference between the vulnerability assessment and the penetration test is that you do not go beyond finding the vulnerabilities in a vulnerability assessment process. You don't try to gain access or maintain the access you gained and all that. So you won't be sure whether or not the finding really exists or, very important, if it's a false positive. Now, you may find some explanations where vulnerability scanning and vulnerability assessment are used for the same reason. However, as you know now, vulnerability assessment is a process that covers the vulnerability scanning. A vulnerability assessment basically consists of the following steps. Identify assets and build an asset inventory. Do you know what the asset is? No worries. Just wait for the next slide. Be patient, my young apprentice. Categorize assets into groups. Scan assets for known vulnerabilities. Rank the risks. Manage the remediation process. And perform follow-up remediation scans to be sure that they're gone. There are tons of systems and services in an IT network. You should scan all the hosts and services of your IT system. Manual scan is, well, almost impossible in practice. So thankfully, we have vulnerability scanners or vulnerability assessment tools, which help you to follow the other steps of the assessment. Qualys, Nessus, and Nexpose are three of the most popular vulnerability scanners. These are commercial tools. Although they have a free community edition, you will have to pay to use all of the functionalities of the tools. OpenVAS, Open Vulnerability Assessment System, is a free and open source tool supported by a pretty good community. So throughout the course, we're going to be using some particular terminology quite often. So it's better if we just define them up front, and then that way if you get to know them now, you won't be running the glossary every time you come across it. So here we have the asset. People, property, and information. People may include the employees or the customers, along with other invited persons, such as contractors or guests. Property assets consist of both tangible and intangible items that can be assigned a value. Intangible assets include reputation as well as proprietary information. The information itself may include databases, software codes, critical company records, and many other intangible items. In short, an asset is what we are trying to protect. Threat. Anything that can exploit a vulnerability, intentionally or accidentally, and obtain, damage, or destroy an asset. In other words, a threat is what we're trying to protect against. Vulnerability. Weaknesses or gaps in a security program that can be exploited by threats to gain unauthorized access to an asset. A vulnerability is a weakness or gap in our protection efforts. Risk. The potential for loss, damage, or destruction of an asset as a result of a threat exploiting a vulnerability. Risk is the intersection of assets, threats, and vulnerabilities. So why is it so important to understand the difference between these terms? In my opinion, if you don't understand that difference, very specifically, you'll never understand the true risk to the assets at stake. You see, when conducting a risk assessment, the formula used to determine risk is A plus T plus V equals R. That is, asset plus threat plus vulnerability equals risk. Exploit. Literally, it should be defined as a piece of software or a sequence of commands that takes advantage of a vulnerability to cause unintended or unanticipated behavior to occur on computer software or hardware. But I'd like to take a moment to explain it in these words. An exploit is an attack on a computer system, especially one that takes advantage of a particular vulnerability the system has or is known for. Used as a verb, exploit refers to the act of successfully making such an attack. Now, one of the basic questions of a penetration test is, what should a pen tester, I think you understand the word by now, the person who performs the pen test, what should the pen tester know about the system that he or she will test? There are typically different approaches according to the knowledge that the pen testers have. A black box pen test requires no previous information and usually takes the approach of an uninformed attacker. In a black box pen test, the pen tester has no previous information about the target system. White box testing is a pen testing approach that uses the knowledge of the internals of the target system, to elaborate the test cases. For example, in application pen testing, the source code of the application is usually provided along with design information. Or in an infrastructure pen test, network maps, infrastructure details, etc. are provided. The goal of a white box pen test is to provide as much information as possible to the pen tester so that he or she can gain insight, understanding of the system, and elaborate the test based on that. Of course, each approach has some advantages as well as some disadvantages, so let's have a look at that now. The advantage of a black box pen test is that it simulates a very realistic scenario. And these are the disadvantages of the black box pen test. Testing time cannot be maximized in certain scenarios. Some areas of the infrastructure might remain untested. The advantages of a white box pen test are you can perform a deep and thorough test. It maximizes the testing time, so you don't need to spend time to find out the system information. It extends the testing area, where black box testing cannot reach, such as the quality of code, application design, etc. Now, some people might think that the white box approach is not realistic, as the pen tester is, just not in the same position as a non-informed potential attacker. Don't agree with this, though, because there might be some inside attackers, or a hacker might have access on an insider's computer, and he or she can potentially learn all the information of the system. Got it? So these are the steps you should take while planning a pen test. We'll see them here in detail. The first step of planning a pen test is to identify the needs of the customer. Here I use the word customer as the owner of the IT system that you perform a pen test for. Of course, the customer's basic need is to identify weaknesses in the information system and take measures before a real attack occurs. But here we should find the methods and targets according to the customer's sensitive topics. For example, who is the most important threat for the customer? An insider, an employee of that company, or an outsider? What is the most important asset that the customer wants to protect? A customer database, financial records, etc., etc. From physical security to web applications, there are a lot of different topics and infrastructures that may be subject to the pen test. There are a few factors to decide the scope of the pen test. The first factor, of course, is asset groups of the customer. And by that I mean you cannot test the wireless systems if the customer doesn't have a wireless network, right? But generally speaking, of course the customer will decide the scope, but please remember, in most cases, you should guide them to decide the correct scope. You should prepare everything you'll need in the pen test. In addition, you should inform the company to be prepared for the pen test as well. On the pen tester side, you'll need the attacker system such as laptop, external disks, USB sticks, etc. And you should be sure that all the necessary applications are installed on these systems. As another important part of preparation, do not forget to install and update the software tools that you'll be using. Just double check. On the other hand, advise the owner of the IT system to have the following setups before the pen test. Monitoring solution. To detect the attacks is as important as to prevent them. In addition, monitoring will let them know what you do throughout the pen test. Since all the pen tests have some risks, it would be better that the owner of the IT system have an up-to-date backup so that they can prevent any possible data loss. And lastly, you should be ready for a service interruption during the pen test, so help the system owner to prepare an emergency response plan. Now, of course, we cannot perform everything we want during the test. Since we are under the rules of an agreement, we do have some restrictions. But please don't forget that the actions we perform in a pen test are totally illegal unless we have an agreement with the legal system owner, right? So these restrictions are mostly defined in the rules of engagement and, of course, in the non-disclosure agreement. A non-disclosure agreement, NDA, is a legal contract between the pen tester and the system owner, that outlines confidential information that the parties wish to restrict access to or by third parties. You will probably access the most critical and confidential data of the system owner, so this agreement is very important, especially for the system owner. Rules of engagement will decide the limits of the pen test. It basically decides the scope, total test duration, the times that the attacks will be performed, and the methods to be used. For example, you should identify whether the DDoS, the denial of service attacks, will be performed as part of a pen test. If it will be performed, the owner is probably going to ask you to perform the attack probably at midnight of a particular weekend. A penetration test briefly consists of 5 phases. Reconnaissance. Now that's the act of gathering preliminary data or intelligence on your target. The data is gathered in order to better plan for your attack. The phase of scanning requires the application of technical tools to gather further intelligence on your target. But in this case, the intel being sought is more commonly about the systems that they have in place. A good example would be the use of a vulnerability scanner on a target network. Exploitation. That's the phase that's also known as gaining access. It requires taking control of one or more network devices in order to either extract data from the target or to use that device to then launch attacks on other targets. The purpose of the post-exploitation phase is to determine the value of the machine compromised and to maintain control of the machine for later use. The value of the machine is determined by the sensitivity of the data stored on it and the machine's usefulness in further compromising the network. Now, covering tracks simply means that the attacker must take steps necessary to remove all semblance of detection. Any changes that were made, authorizations that were escalated, etc., all must return to a state of non-recognition by the host network's administrators. Reporting is the proof of your actions performed during the pen test. It's where you're going to report the findings and share recommendations to remediate the vulnerabilities and weaknesses. So let's have a look at these phases in detail. Reconnaissance. As you already know, it's the act of gathering preliminary data or intelligence on your target. The data is gathered in order to better plan for your attack. The success of the pen test depends on the accuracy of your reconnaissance. A pen tester works on gathering as much intelligence on the client organization and the potential targets for exploit as possible. We can classify the scanning activities into 2 main parts. The network scan is used to discover devices such as end-user computers, servers, and peripherals that exist on a network. Results can include details of the discovered devices, including IP addresses, device names, operating systems, running applications and services, open shares, usernames, and groups. Since we gather information about the network and system, this process is often related to the reconnaissance phase as well. A vulnerability scan detects and classifies system weaknesses in computers, networks, and communications equipment, and predicts the effectiveness of countermeasures. Now, since there are thousands of different systems and services, we should perform thousands of analyses to understand whether or not a service has vulnerabilities. And the vulnerability scanners are used to automate this process. Makes your job a whole lot easier. Exploitation. That's the phase that requires taking control of one or more network devices in order to either extract data from the target or to use that device to then launch attacks on other targets. The purpose of the post-exploitation phase is to determine the value of the machine compromised and to maintain control of the machine for later use. The value of the machine is determined by the sensitivity of the data stored on it and the machine's usefulness in further compromising the network. Now I've got your attention. The final phase before reporting is covering your tracks. It's basically returning everything to the initial state, the state before the pen test. Now, since you have limited time to perform the pen test, you might ask the system owner to define some privileges and exceptions for you. If so, you should remind them to remove these exceptions at the end of the pen test. And in addition, you will probably make a lot of changes during the pen test, such as adding a new user to the domain admin group or create a backdoor into a compromised system for later use. It's very important to remove all these changes at the end of the pen test. Otherwise, the black hat hackers can compromise the systems using these modifications. The report is the fruit of the pen test. It's the outcome of the actions you performed throughout the pen test. A pen test report typically consists of the following sections. An introduction. What's the purpose, the scope, and the duration of the test? A management summary, the screenshot of the IT system to show how vulnerable it is. The findings section that lists all of the vulnerabilities found during the pen test. And the recommendation section includes just how the owner can harden the system. Now, it's obvious that the findings is going to be the most important section of the pen test report, especially to the owner. The system owner will see the weaknesses here and remediate them according to your recommendations. So you should give at least the following details about the findings. A short name of the vulnerability to give brief information about it. The severity level of the vulnerability. That'll help the system owner to triage the remediation process. The list of vulnerable assets. Which assets in particular have this vulnerability? A detailed explanation of the vulnerability to show the possible consequences. A brief summary of how you identified the vulnerability. And support this section with screenshots wherever possible. Recommendations to remediate or at least mitigate the vulnerability. And finally, share the references about the vulnerability to let the system owner find out more about it. Before beginning a pen test, the parties should enter into a contract indicating exactly what the pen testers will do and will not do, and the range of IP addresses, subnets, computers, networks, or devices that will be the subject of the pen test. The pen tester should obtain a get-out-of-jail-free card from the customer, specifically indicating not only that the pen testing is authorized, but also indicating that the customer has the legal authority to authorize the pen test. Big distinction, and very important. If a cloud customer authorizes a pen tester to test their network in the cloud, this does not mean that the cloud provider has authorized the test. The cloud provider could go after the pen tester for unauthorized access. A non-disclosure agreement, NDA. It's also known as a confidentiality agreement. It's a legal contract between the pen tester and the system owner that outlines confidential material, knowledge, or information that the parties wish to share with one another for certain purposes, but wish to restrict access to or by third parties. As I mentioned before, you will probably access the most critical and confidential data of the system owner. So this agreement is very important, especially for the system owner. Now, since penetration tests are very important for cybersecurity, it'd be very good to have some standards while performing the test steps. And thankfully, we have several organizations and consortiums to identify the standards. The best-known ones are PCI DSS. It's the Payment Card Industry Data Security Standard. PCI DSS is the worldwide payment card industry data security standard that was set up to help businesses process card payments securely and reduce card fraud. Sad but true fact here that money seems to be the most important thing for human beings, so these guys identify the standards of cybersecurity. OWASP is the Open Web Application Security Project. It's a worldwide, not-for-profit charitable organization focused on improving the security of software. So you can find standards of application security right here. PTES, Penetration Testing Execution Standard, was started as the brainchild of 6 information security consultants attempting to address deficiencies in the penetration testing community in 2009. Pentest helps penetration testers adhere to best practices, so check them out. OSSTMM, Open Source Security Testing Methodology Manual, is methodology to test the operational security of physical locations, workflow, human security testing, physical security testing, wireless security testing, telecommunications security testing, data network security testing, and compliance. NIST, the National Institute of Standards and Technology. It's a physical sciences laboratory and a non-regulatory agency of the United States Department of Commerce. Its mission is to promote innovation and industrial competitiveness. They're very good at defining standards, though. SB 800-115 is a technical guide to information security testing and assessment. The purpose of this document is to assist organizations in planning and conducting technical information security tests and examinations, analyzing findings, and developing mitigation strategies. So let's look at the basic concepts of networking, and of course, the mother of all networks, the Internet. The Internet is a global system of interconnected computer networks that use the standard Internet Protocol Suite, often called TCP/IP, although not all applications use TCP, to serve billions of users worldwide. It's a network of networks that consists of millions of private, public, academic, business, and government networks of local to global scope that are linked by a broad array of electronic, wireless, and optical networking technologies. The Internet carries an extensive range of information resources and services, such as the interlinked hypertext documents of the World Wide Web, WWW, and the infrastructure to support email. The origins of the Internet reach back to research done in the 1960s, commissioned by the United States government in collaboration with private and commercial interests to build robust, fault-tolerant, and distributed computer networks. The primary precursor network, the ARPANET, initially served as a backbone for interconnection of regional academic and military networks in the 1980s. The funding of a new U.S. backbone by the National Science Foundation in the 1980s, as well as private funding for other commercial backbones, led to worldwide participation in the development of new networking technologies and the merger of many networks. The commercialization of what was by the 1990s an international network resulted in its popularization and incorporation into virtually, I'd say, every aspect of modern human life. So as of 31st December 2017, more than 4.1 billion people, nearly 55% of the whole world population, use the services of the Internet. Now, I'll put that in a little perspective here. That's 95% of North Americans and about 85% of Europeans are Internet users. Now, before talking about the Internet Protocol, or what we call IP, we should know what a protocol actually is. A protocol is simply a set of rules governing how things work in a certain technology, so that there is some kind of standardization. Protocols are also typically in charge of sending the right data to the right PC, making sure the data gets to the right program, as well as organizing the data to be sent. Protocols are to computers what language is to humans. For instance, this course is in English. To understand it, you must be able to understand English. So similarly, for two devices on a network to successfully communicate, they must both understand the same protocols. So I know we're going to talk about this in detail later, but we'll talk a little bit now about IP to better understand the Internet. Internet Protocol, IP, describes how data packets move through a network. So when you have a protocol, you are sure that all machines on a network, or in the world when it comes to the Internet, however different they might be, speak the same language and can integrate into the whole framework. The IP protocol standardizes the way machines over the Internet or any IP network forward or route their packets based on their IP addresses. So along with addressing, routing is one of the main functions of the IP protocol. Routing consists of forwarding IP packets from source to destination machines over a network based on their IP addresses. An IP address is a unique address identifying a machine, which can be a computer, a server, an electronic device, a router, a phone, you name it, on a network, thus serving, routing, and forwarding IP packets from source to destination. Basically, every computer connected to the Internet is given an IP address by the Internet service provider, and the computer becomes accessible to others via this IP address. So let's see what the Internet looks like on its most basic level. Here we have a home network with a router, given by the Internet service provider, or ISP. Remember that modem that's given to you by your ISP, and the devices it connects to the Internet. This is a corporation with a lot of end-user computers and servers as well. There's a public body here, again, with a lot of servers and a lot of end-user computers. Here is a hosting company with a web server farm hosting to their customers. Now here's a cloud provider such as Amazon Web Services, hosting a lot of servers again. And here there's another home, and they're all connected to each other over telecom company routers. Reference models are conceptual frameworks for understanding relationships. The purpose of the reference models are to guide vendors and developers so that digital communication products and software programs they create can interoperate and facilitate clear frameworks that describe the functions of a networking or telecommunication system. OSI, Open Systems Interconnection, is a reference model for how applications can communicate over a network. A reference model is a conceptual framework for understanding relationships. The purpose of the OSI reference model is to guide vendors and developers so that the digital communication products and software programs they create will interoperate and to facilitate clear comparisons among communications tools. Most vendors involved in the telecommunications make an attempt to describe their products and services in relation to the OSI model. And although useful for guiding discussion and evaluation, OSI is rarely actually implemented, as few network products or standard tools keep all related functions together in well-defined layers as related to the model. Developed by representatives of major computer and telecommunication companies beginning in 1983, OSI was originally intended to be a detailed specification of actual interfaces. Instead, the committee decided to establish a common reference model for which others could then develop detailed interfaces, which in turn could become standards. OSI was officially adopted as the international standard by the International Organization of Standards, ISO. So what about the OSI layers? The main concept of OSI is that the process of communication between two endpoints in a telecommunication network can be divided into 7 distinct groups of related functions, or layers. Each communicating user or program is at a computer that can provide those 7 layers of function. So, in a given message between users, there will be a flow of data down through the layers in the source computer, across the network, and then up through the layers in the receiving computer. The 7 layers of function are provided by a combination of applications, operating systems, network card device drivers, and networking hardware that enable a system to put a signal on a network cable or out over Wi-Fi or any other wireless protocol. The 7 open systems interconnection layers are: Layer 7, the application layer. This is a layer at which communication partners are identified. Is there someone to talk to? Network capacity is assessed. Will the network let me talk to them right now? And it creates a thing to send or opens the thing received. Please note that this layer is not the application itself. It is the set of services an application should be able to make use of directly, although some applications may perform application layer functions. Layer 6, the presentation layer. This layer is usually part of an operating system and converts incoming and outgoing data from one presentation format to another. For example, from clear text to encrypted text at one end and back to clear text at the other. Layer 5, the session layer. This layer sets up, coordinates, and terminates conversations. Services include authentication and reconnection after an interruption. On the Internet, Transmission Control Protocol, TCP, and User Datagram Protocol, UDP, provide these services for most applications. Layer 4, the transport layer. This layer manages packetization of data, then the delivery of the packets, including checking for errors in the data once it arrives. On the Internet, TCP and UDP provide these services for most applications as well. Layer 3, the network layer. This layer handles the addressing and routing of the data, sending it in the right direction to the right destination on outgoing transmissions, and receiving incoming transmissions at the packet level. IP is the network layer for the Internet. Layer 2, the data link layer. This layer sets up links across the physical network, putting packets into network frames. This layer has two sublayers, the logical link control layer and the media access control layer. Ethernet is the main data link layer in use. Layer 1, the physical layer. This layer conveys the bit stream through the network at the electrical, optical, or radio level. It provides the hardware means of sending and receiving data on a carrier network. Let's see some of the most famous protocols of the layers. For ease of use, it's better to talk about physical layer and data link layer together. Here we have some protocols in data link layer and some physical media and connection methodologies in physical layer. Ethernet and 802.11 wireless LAN are the most known protocols of the data link layer. Ethernet is the name of the most commonly used network protocol that controls how data is transmitted over a LAN, which is a local area network. You need to have network interface cards in the devices that you want to connect to the network. A wireless local area network, WLAN, is a wireless computer network protocol that links two or more devices using wireless communication within a limited area such as a home, school, computer laboratory, or office building. This gives users the ability to move around with a local coverage area and yet still be connected to the network. Most modern WLANs are based on IEEE 802.11 standards and are marketed under the Wi-Fi brand name. IP, Internet Protocol, is responsible for addressing hosts, encapsulating data into transferred packets, and routing packets from a source host to a destination host across one or more IP networks. The best-known transport protocol is the Transmission Control Protocol, or TCP. It's used for connection-oriented transmissions, whereas the connectionless User Datagram Protocol, UDP, is used for simpler messaging transmissions. We're going to talk more in depth about these protocols in the next lecture. Again, for ease of use, the last three layers, session layer, presentation layer, and application layer, are thought of together as the application layer. Let me put another parenthesis here. We're talking about the OSI reference model here. In addition, there is another reference model called TCP/IP reference model. And instead of OSI model's last three layers, there is only a single application layer in the TCP/IP reference model. Just keep that in the back of your mind. And back to our subject. The application layer protocols are classified according to the protocol they are using in the transport layer. And these protocols interact with the end user via applications. Therefore, they are the most known protocols by just about everybody. Some of the most well-known TCP-based application layer protocols are HTTP, Hypertext Transfer Protocol, simply a communications protocol used to send and receive web pages and files on the Internet. Telnet is one of the simplest ways to exchange data between two computers. It allows two computers anywhere on a computer network, including the worldwide Internet, to exchange text and, other data in real time. FTP, File Transfer Protocol, is a communication protocol for the rapid, simple transmission of files across a network. SMTP, Simple Mail Transfer Protocol, is used to send and relay an email message between email servers. Note that it is not used to retrieve email messages from a server. Instead, either IMAP or POP is used to retrieve email messages. DNS, the Domain Name System, is a system used to convert a computer's host name into an IP address on the Internet. For example, if a computer needs to communicate with a web server, nhs.uk, your computer needs the IP address of the web server, nhs.uk. It is the job of the DNS to convert the host name to the IP address of the web server. The DNS uses both the UDP and TCP. SNMP, Simple Network Management Protocol, is used in network management systems to monitor status of devices and also spot problems. So let's see what happens to a packet inside the network traffic. Please note, the data unit transferred between two endpoints has different names in each layer. In layers 5, 6, and 7, application layers, it's called data. In layer 4, transport layer, it's called segment for TCP and datagram for UDP. In layer 3, the network layer, it's called packet. In layer 2, the data link layer, the data unit is called frame. Now, I usually use packet for the transferred data unit in each layer to make it less complicated for you. Make sense? Before looking at the road trip of a DNS query in detail, let's look at the relationship between the OSI layers and computer systems. The packets in layer 1 and layer 2 are managed by network interfaces of your device, for example, by your Ethernet card. And the packets from 3 to 7 are managed by the processing unit. In software detail, the layer 3 and layer 4 packets are managed by the operating system of your devices. And the packets of layer 5 to 7 are managed by the related application or service, for example, a web browser. When you write a URL in the address bar of your browser and hit enter, the first thing it sends is a DNS query. A DNS query is the process of a computer networking device making an inquiry to get an IP address for a DNS name such as mail.yahoo.com. The client computer will send a DNS query to one of their Internet Service Provider's DNS servers. The DNS server looks in its DNS database to tell whether it can answer the query authoritatively. If the DNS server can answer authoritatively, the DNS server answers the query and the DNS query process is complete. So let's see the road trip of a DNS query from your computer to a DNS server. When data is transmitted by the source toward a specific destination, it passes through the application, presentation, and session layers, and the protocol data unit arrives at the transport layer, layer 4. Layers 5, 6, and 7 are displayed as a single layer to simplify the presentation. At this layer, a 20-byte data header is placed in front of the data. A DNS query can also use TCP, but let's assume that it uses UDP at this time. The data and the layer 4 header, here it's UDP header, which together form a segment or datagram, is passed down to layer 3, the network layer. The network layer places its layer 3 header, here the IP header, in front of the received segment, and this group becomes a packet. The layer 3 header contains important fields such as the logical address, the IP address, of both the source and the destination device. The newly formed packet is then passed down to layer 2. The data link layer creates a new data unit called a frame by adding the layer 2 frame header, which is the Ethernet header here. Like layer 3, an addressing structure is also applied in the layer 2 header. That is the MAC address. The frame is then passed down to the physical layer, which converts the information into 0 and 1 bits that are sent over the physical media using electrical signals, on a copper link, for instance. Finally, the data is sent over the wire using a wide variety of methods, such as Ethernet or token ring. The headers are a specific form of control information that allows the data to go through the network properly. Thus, the data at each layer is encapsulated in the information appropriate for the specific layer, including addressing and error checking. The overall size of the information increases as the data travels through the lower layers from layer 4 to layer 1. The destination device, which is the DNS server here, receives the data, and this additional information is analyzed and then is removed as the data passes through the higher layers up to the application layer, where the data is decapsulated. The TCP/IP model is a model with 4 layers, which is for both modeling current Internet architecture, as well as providing a set of rules that govern all forms of transmission over a network. DARPA, an agency of the United States Department of Defense, created it in the 1970s. This model was being made at the same time the OSI model was created. The TCP/IP model is not the same as the OSI model, however. It was influenced by the model, which is why many of the names of the different layers are the same. So we can simply say that the TCP/IP reference model represents reality in the real world, whereas the OSI reference model represents an ideal. Okay? So these are the main differences of the TCP/IP reference model. The three top layers in the OSI model, that is the application layer, the presentation layer, and the session layer, are not distinguished separately in the TCP/IP model, which only has an application layer above the transport layer. TCP corresponds to OSI layer 4, the transport layer. IP corresponds to a subset of OSI layer 3, the network layer. TCP/IP makes no prescriptions as to the link layers below IP, while OSI specifies two layers. The physical address, commonly the MAC address, which is located in a special field in the data link layer header, changes as the packet passes from one device to another. For example, from the source PC to a switch, to a router, to another switch, and then finally to the destination PC. However, the original IP source and destination addresses do not change when transiting the network because the packet is stripped of its layer 3 header only when it goes beyond a router. When it stays within the same LAN, it only passes through switches, which decapsulate it at the layer 2 header containing the MAC address. So as a result, the header changes as the packet is re-encapsulated, as does the MAC address fields. So let's examine the packets and protocols with Wireshark. Wireshark is a free, open source, and it's the world's foremost network packet analyzer. And it's also the de facto standard across system and network administrators. Wireshark has the ability to listen and record traffic, as well as contains some pretty advanced filtering and reviewing options. So first I'm going to visit an HTTP website, and then an HTTPS website. Let's go to Kali and run Wireshark. You can open a terminal screen and type Wireshark to start it. So these are the network interfaces that Wireshark is able to listen to. Maybe open another terminal screen and run the ifconfig command to see the network interfaces. So as you know, ifconfig stands for network interface configuration. So if we use the command without any parameter, it'll list all the interfaces available. We have eth0 as a network interface to listen to. So now I'll turn back to Wireshark and double-click eth0 to select it. Now Wireshark starts to listen to the Ethernet interface of Kali. And to create some traffic, I'll open a web browser and just visit an arbitrary website. And now we have enough packets to examine, so I'll click the Stop button at the upper left corner of Wireshark to stop listening to the traffic. So first, we have some DNS packets to find out the IP address of the visited site. We'll look at these kinds of packets soon, but right now let's just have a brief look. So a DNS query for the IP version 4, another DNS query for IP version 6. Don't worry about the versions right now, we'll cover them soon, I promise. These DNS queries are transferred as UDP packets in transport layer. The destination port is 53. This is the IP packet with the source and the destination IP addresses. So we'll go through the layers one by one, and we'll see all these packets, datagrams, and frames in detail. So we'll keep going. This is the structure of the Ethernet frame. First, there are two DNS queries for www.hackeracademy.uk. One for the IPv4 address, and the other one is for the IPv6 address. And because the website is redirected to hackeracademy.uk, there are two more DNS requests for this address. Next, DNS packets are the DNS query responses. This response is type A. That means it's an answer for the IPv4 request. And here's the answer, the IP address of the website. Now, DNS response packet uses UDP at the transport layer, IP at the network layer, etc. Here we have a TCP handshake between Kali and the web server. We'll also see this in detail later on. A SYN packet, a SYN ACK as a reply, and an ACK packet to complete the handshake. This is an HTTP GET request. We learned the IP address of the website, and now the system is ready to receive the web page. HTTP protocol and application layer. Now you can see the headers and the parameters of the request. TCP protocol and transport layer, source port, destination port, flags, etc. IP protocol in network layer. Here are the source and destination addresses. And Ethernet frame in layer 2. These are the TCP packets, which will build the HTTP response. So in this example, it's the web page. In other words, the response is transferred between the web server and our system as fragmented packets in transport layer. Here's the HTTP response, 200, okay. So the web page is received. And here's the data, which is our web page. These are the response details, response type, headers, etc. Here, there's additional information produced by Wireshark, which says that the HTTP response is created by reassembling 5 TCP segments or packets. So now, I'd like to show you the difference between that and HTTPS traffic. So I'll go to the browser and visit an HTTPS page now. But before visiting the page, let's start Wireshark. Here's the start button. Continue without saving. Okay, now we have a clean sheet. So I'll go to the browser and hit enter. Wow, lots of packets in milliseconds. So we've got plenty of packets to investigate. Just click the stop button once again. Okay, so the DNS request and the response packets first. Here is a response with an IPv4 address. Here there's a TCP three-way handshake between Kali and port 443 of Google's web server. And now a client hello TLS packet to start the TLS handshake, again between Kali and Google's server. Now to get rid of the other traffic records, I'd like to filter the results by the IP address of the Google server. Now, while the mouse pointer is on the server IP address, right-click and go to Apply as Filter and select the Selected option. So as you can see here in the filter bar, the IP address is assigned as the destination IP address. Now, we only have to see the traffic where the destination is the Google server. But we'd like to see both the incoming and the outgoing traffic. So I'll change the DST part of the filter to ADDR and click the blue arrow to activate the new filter. Now we can see the traffic in both directions. Okay, so here we are at the Hello TLS message. Here are the details of the message. TLS uses TCP protocol in transport layer. The Google server replies a server hello message as the second step of the TLS handshake. Then comes the certificate and server key exchange, and the server hello done message is sent by the server. Kali sends the client key exchange, Google server sends the new session ticket, and the encrypted communication starts. Here is some encrypted application data, which is meaningless for others who listen to the traffic. And as you can see here, the message is encrypted at the application layer, so you can still see the source and the destination addresses, the ports, etc. All right, so since there's really nothing much to say about the physical layer, because in this course we're really looking at the digital side of networking, I'd like to just skip that and start with the second one, the data link layer. The data link layer is the second layer in the OSI, Open Systems Interconnection, 7-layer reference model. Now, it responds to service requests from the network layer above it and issues service requests to the physical layer below it, right? So the data link layer is responsible for encoding bits into packets prior to transmission, and then decoding the packets back into bits at the destination. And bits, by the way, are the most basic unit of information in computing and communications. Packets are the fundamental unit of information transport in all modern computer networks, and increasingly in other communications networks as well. So the data link layer is also responsible for logical link control, media access control, hardware addressing, error detection, and handling and defining physical layer standards. It provides reliable data transfer by transmitting packets with the necessary synchronization, error control, and flow control. The data link layer is divided into two sublayers. First, the media access control, MAC, sublayer, that governs protocol access to the physical network medium. Through the MAC addresses that are typically assigned to all ports on a router, multiple devices on the same physical link can uniquely identify one another at the data link layer. MAC addresses are used in addition to the network addresses that are typically configured manually on ports within a network. Now, secondly, the Logical Link Control, or LLC sublayer, manages communications between devices over a single link of a network. This sublayer supports fields in link layer frames that enable multiple higher layer protocols to share a single physical link. So here we have some protocols in the data link layer and some physical media and connection methodologies in the physical layer. Ethernet and 802.11 wireless LAN are the best known protocols of the data link layer. Ethernet is the name of the most commonly used network protocol that controls how data is transmitted over a LAN, which is a local area network. Now, you need to have a network interface card in the device that you want to connect to the network. I know it probably seems pretty obvious to you, but I just wanted to make sure that we're all on the same page. A wireless local area network, or WLAN, is a wireless computer network protocol that links two or more devices using wireless communication within a limited area, such as a home or school, computer lab, or office building. Now, this gives users the ability to move around within a local coverage area and still be connected to the network. Most modern WLANs are based on the IEEE 802.11 standard and are marketed under the Wi-Fi brand name. So Ethernet has been a relatively inexpensive, reasonably fast, and very popular LAN technology for, several decades. It was commercially introduced in 1980 and first standardized in 1983 as IEEE 802.3. And has since been refined to support higher bit rates and longer link distances. Ethernet has since become the most popular and probably the most widely deployed network technology in the world. Many of the issues involved with Ethernet are common to many network technologies, and understanding how Ethernet addresses these issues can build a foundation that will improve your understanding of networking in general. So let's keep the design principles of Ethernet simple. The basic idea of its design is that multiple computers have access to it and can send data at any time. If two computers send data at the same time, a collision will occur. And when this happens, the data sent is not going to be usable. In general, both computers will stop sending and wait a random amount of time before they'll try again. Now, a special protocol was developed to deal with such problems. It's called Carrier Sense Multiple Access with Collision Detection, or it might be easier to say CSMACD. Today, Ethernet cables look like, thick telephone cables. Modern cables connect to hubs or switches, and each cable runs from a computer's network interface card, the NIC, to such a box. Now, here are the most widely known Ethernet cables. 10-base-2 and 10-base-5 cables are what I would call retro coaxial cables. You don't see them much today. Each computer has a T plugged into it, and cables plug into each side of that T. 10-base-T, 100-base-T, 1000-base-T are all unshielded twisted pair, or UTP cables, which look a lot like thick phone cables, and they go from each computer to a hub or a switch. Initial numbers indicate the supported speed, so the 10 will stand for 10 megabits per second, and 1000 stands for 1000 megabits, also known as gigabit or 1 gigabit. 10-base-F cables are the same as 10-base-T, but they are fiber cables, and they'll transmit light pulses instead of electrical signals over copper. A data packet on an Ethernet link is called an Ethernet packet, which transports an Ethernet frame as its payload. An Ethernet frame is preceded by a preamble and start frame delimiter, or SFD, which are both part of the Ethernet packet at the physical layer, right? There are 4 types of Ethernet frames, and the most common one is the Ethernet 2 frame, also known as DICS frame. We're talking about the Ethernet 2 frame at the moment. Each Ethernet frame starts with an Ethernet header, which contains destination and source MAC addresses as its first 2 fields. The middle section of the frame is payload data, including any headers for other protocols, for example, Internet Protocol, carried in the frame. The frame ends with a frame check sequence, or FCS, which is a 32-bit cyclic redundancy check used to detect any in-transit corruption of data. Address Resolution Protocol, ARP, is a network layer protocol used for mapping a network address such as an IPv4 address to a physical address such as a MAC address. To simulate how the ARP mechanism works, we have a small network in the slide, a switch on top, and 3 computers connected to it. Computer A wants to talk to computer C. It puts an ARP request onto the wire, which happens to be broadcast. Essentially what it's saying is, who has computer C's MAC address? Of course, because it's a broadcast, every system on the network hears it. Does everybody respond? Well, what happens is that B hears that A is looking for the MAC address of computer C. B knows that it's not computer C and therefore does not respond to the broadcast. The broadcast, the ARP request, goes out to every system, but the only system that will reply is computer C with an ARP reply. In other words, computer A says, who has the MAC address of computer C? And although all the workstations hear the question, only C replies and says, I've got the MAC address of computer C, and this is what it is. So the ARP reply sends back the MAC address to computer A, and each of these machines start building an ARP table. So what is the ARP table? Since computers cannot send broadcast messages every time they need to connect with another network device, they store the IP addresses and the corresponding MAC addresses of systems they frequently communicate with in a table called ARP table. All the systems in the LAN maintain this table. The entries in the ARP cache table are generally short-lived and are updated every 15 to 20 minutes. Now let's get back to our topic. Can we say that one of the passive scan methods is just looking into the ARP table of a system, which is a network that we are scanning? Well, sure we can. Inside an ARP table, we see the IP addresses of some of the systems of the network and their corresponding MAC addresses. Let's see the ARP tables in 3 different platforms: Mac OS, Windows, and Debian Linux. We are in a Mac OS operating system first. Open the terminal first. Type terminal in the search box of the applications window, which brings you the terminal application. Typing ARP and hitting enter shows a small help for ARP command. If you want to see detailed help about the ARP command, you can use MAN command. Type MAN, ARP, and hit enter. You'll get detailed help. A parameter is used to display all current ARP table entries. But hold on, it says A is used to delete all entries as well. How can that be? Well, to delete an ARP table entry, you use D parameter. If you use this parameter with A parameter, you are able to delete all entries of ARP tables. I parameter is used to see the entries of a single interface. By default, ARP command tries to show the display addresses symbolically. To see the IP addresses instead of display names of the systems, you have to use N parameter, which means do not resolve names. Okay, press Q to quit the man page of the ARP command. Now type ARP-AN to see all the entries of the ARP table. Since Mac OS is a BSD-based operating system, the results of the ARP command is displayed in BSD style. Second machine is a Microsoft Windows 8. Let's open a command prompt first. I have a shortcut on my status bar, so I click it to start a command prompt. Alternatively, press Windows plus R buttons, open the dialog box, run Command, and hit Enter. If you type ARP in a Windows system, the help page of ARP command is displayed. Type ARP-A to see the entries of the ARP table. In my opinion, this display is more, human readable than BSD style. Now, although we're not interested in these at the moment, I would like to talk a little about the IP addresses that start with 224 to calm your curiosity. 224.0.0.22 is the multicast address for Internet Group Management Protocol. 224.0.0.252 is used by recent versions of Windows for Link Local Multicast Name Resolution, LLMNR, searching for local network computers. The third machine is our Kali, which is a Debian-based Linux operating system. Open the terminal window. If you type ARP and hit Enter, the ARP table entries are displayed in a human-readable format. As you see, systems are listed with a known domain name such as www.owaspbwa.com by default. ARP-H brings you a small help page. If you want a detailed help page, type man space ARP. In a Debian-based Linux system, -A parameter of ARP command is used to see the entries in BSD format, which we saw in macOS. -I is, again, to see the entries of a single interface. Okay, press Q to quit the man page. ARP-A displays ARP table entries in BSD format, and use N parameter to see the IP addresses instead of domain names of the systems. So let's see how the ARP packets are seen in Wireshark. To see the ARP packets, we must first force the system to send an ARP request. Then we can have a close look into the fields of the ARP packets. So I'm in Kali, and I want to look at the ARP table first. So I'll open a terminal browser and type ARP. So this is the ARP table of my Kali. There are two records at the moment, one for the gateway and one for the VM with the IP address of 207. So let's clear the table first. Now I don't have to delete the records of the ARP table, so I can use the H parameter to get help. So it tells me to use the D parameter to delete a specified entry. Now, does it delete all the entries if I don't specify any particular one? So I'll use the D parameter with no value, and it needs the host name. Okay, so I delete the entry for VM207, so I can push it to create an ARP request. Okay, deleted the entry. Now I'll run Wireshark. Now remember, we run Wireshark within the terminal screen just as before. So I'll click Wireshark icon, and that makes it run. So double-click the ETH0 to start capturing the traffic. Okay, now I go to the terminal screen and ping VM207, turn back to the Wireshark interface, and since we have enough packets to examine, let me just stop capturing. So let's look at the first packet. It's an ARP request. When we ping the IP address 172.16.99.207, since Kali doesn't know who has this address, it broadcasts an ARP request to learn the owner of the IP. And the second packet is an ARP response. So I go back to the request and expand the ARP packet information block. The sender MAC address and the sender IP address are Kali's addresses. The target MAC address is filled with zeros because, well, we don't know it yet. When we look at the Ethernet frame, we see that the 48-bit destination address is full of ones. All these F letters correspond to these ones in hexadecimal, and the frame is broadcast, right? Now this is the ARP response by VM207. And as you can see, the VM returns its MAC address in the sender MAC address field to Kali. And then, as seen in the table, Kali starts to send the ping requests to VM207. And then VM207 replies to the requests. Talk about clear communication. So before talking about VLANs, I think it's better to give a brief summary of LANs in general. So a LAN is a local area network. It's a group of computers and associated devices that share a common communications line or wireless link to a server. Typically, a LAN encompasses computers within a distinct geographic area, such as an office or a commercial establishment. Computers and other mobile devices use a LAN connection to share resources, such as a printer or even network storage. A virtual local area network, virtual LAN or VLAN, is a group of hosts with a common set of requirements which communicate as if they were attached to the same broadcast domain, regardless of their physical location. So a VLAN has the same attributes as a physical local area network, or LAN, but it allows for end stations to be grouped together even if not on the same network switch, right? VLAN membership can be configured through software instead of physically relocating devices or connections. VLAN is an important topic and it should be included in this course, but why did I put it in this section, the data link layer? Yes, because VLAN is partitioned and isolated in a computer network at the data link layer. Very good. Let's get into that. In this context, virtual refers to a physical object recreated and altered by additional logic. VLANs work by applying tags to network packets and handling these tags in networking systems, creating the appearance and functionality of network traffic that is physically on a single network but acts as if it is split between separate networks. So let's run down some of the primary benefits of using VLANs. So security at the top. Groups that have sensitive data are separated from the rest of the network. Separating systems that have sensitive data from the rest of the network decreases the chances that people will gain access to the information that they're not authorized to see. Cost reduction. Cost savings result from less need for expensive network upgrades and more efficient use of existing bandwidth and uplinks. Higher performance. Careful monitoring of network use allows the network administrator to create VLANs that reduce the number of router hops and increase the apparent bandwidth for network users. Broadcast storm mitigation. So dividing a network into VLANs reduces the number of devices that may participate in a broadcast storm. Since a principal element of a VLAN is the fact that it does not pass broadcast traffic to nodes that are not part of the VLAN, it automatically reduces broadcasts. Improved IT staff efficiency. That's right, VLANs make it easier to manage the network. When you provision a new switch, all the policies and procedures already configured for the particular VLAN are implemented when the ports are assigned. Simpler company management. Companies may want VLAN set up for departments that are heavy network users, such as multimedia or engineering, or a VLAN across departments that is dedicated to specific types of employees, such as managers or salespeople. Excellent. So a wireless network is a computer network that uses wireless data connections between network nodes. Wireless networks are generally implemented and administered using radio communication. And with this method, the costly process of introducing cables into a building can, well, obviously be avoided. A wireless local area network, WLAN, links two or more devices over a short distance using a wireless distribution method, usually providing a connection through an access point for internet access. IEEE 802.11 is a set of MAC and physical layer specifications for implementing wireless LAN computer communication. Now, they're the world's most widely used wireless computer networking standards, used in most home and office networks to allow laptops, printers, smartphones to talk to each other and access the internet without being connected to any wires. So for this, I'm just trying to keep it simple, so I won't talk about the entire 802.11 family or the technical details beneath them. I just want to let you know that the most popular are those defined by the 802.11b and the 802.11g protocols, which are amendments to the original standard. So 802.11-1997 was the first wireless networking standard. But 802.11b was the first widely accepted one, followed by 802.11g and then 802.11n. 802.11n is an amendment that improves upon the previous 802.11 standards by adding multiple input, multiple output antennas, MIMT. So MIMT, it's basically a method for multiplying the capacity of a radio link using multiple transmit and receive antennas. Nowadays, 802.11ac is popular. So it builds on the 802.11n and includes wider channels in the 5 gigahertz band. The segment of the radio frequency spectrum used by 802.11 varies pretty much between countries. For example, in the U.S., 802.11a and 802.11g devices may be operated without a license, as allowed in the regulations. Wireless networks are identified using a Service Set Identifier, or SSID, or I'll call it a SID. An SSID is the primary name associated with an 802.11 wireless LAN, including home networks and public hotspots. Client devices use this name to identify and join wireless networks. Now, there are multiple kinds of SSIDs. Used by itself, the term SSID refers to the name of a wireless network, whether it be a point-to-point network made of only individual wireless clients intercommunicating, or an infrastructure network with clients relying on access points. So getting more specific, we have basic SSIDs, or BSSIDs, which are the MAC address of the access point, the 48-bit number that uniquely identifies every wireless, and every wireline for that matter, network interface. The extended SSID, or ESID, is a unique name applied to one or more access points offering the same service, such as access to a single wireline network. Now, in some deployments, unique ESIDs are applied to each individual access point. In others, all access points that offer access to the same wireline network are given identical ESID values to help foster roaming between the various access points. But generally speaking, when analyzing wireless LANs, we want to discover the BSSID, the MAC address, and the ESID, the name applied to the wireless network as a whole, with a unique value typically applied to each individual access point. Now, since this is a course for penetration testers, we really need to talk about the weaknesses of the wireless network infrastructure. So here are some of the most significant vectors for wireless attacks. Denial of service. Blocking legitimate users on a wireless LAN is trivially easy, even if the network is carefully constructed. Rogue access points. Employees sometimes set up unauthorized access points in an enterprise environment to bypass the legitimate wireless infrastructure or to gain wireless access when such an infrastructure isn't provided by the enterprise. Now, penetration testers and ethical hackers alike are sometimes required to sweep an organization's physical infrastructure to find these unauthorized access points. Lack of or improper configuration of wireless access points. Right, so if access points are not configured appropriately, attackers can have a much easier time of employing any of the rest of these attack vectors. Traffic capture intercept. In a wireless LAN, the hacker can get access to the data link layer, layer 2 communications, as long as he or she is in physical proximity of the device. For merely capturing packets, that proximity for a wireless LAN could be a mile or more. Numerous wireless sniffing tools can be used in such attacks. Crypto attacks. Some wireless encryption protocols suffer from significant security weaknesses, such as the Wired Equivalent Privacy (WEP) protocol. Attackers can gather web traffic and, by exploiting flaws in the way cryptographic initialization vectors are exchanged, crack the keys to gain access to the data and the network. Client duping. Some tests call for a penetration tester or ethical hacker to set up a bogus access point to see if clients will trust it and then use it to access the rest of the network. The attacker can then sit in the middle of all the communications, harvesting them or changing the data as it passes by. The next layer is the third layer of the OSI reference model, the network layer. The network layer provides the means of transferring variable length network packets from a source to a destination host via one or more networks. In other words, the network layer is responsible for packet forwarding, including routing, through intermediate routers. Within the service layering semantics of the OSI network architecture, the network layer responds to the service requests from the transport layer and issues service requests to the data link layer. So here are the functions of the network layer. Connectionless communication. For example, IP is connectionless in that a data packet can travel from a sender to a recipient without the recipient having to send an acknowledgement. Connection-oriented protocols exist at other higher levels of the OSI model. Host addressing. Every host in the network must have a unique address that determines where it is. On the internet, addresses are known as IP addresses, right? Message forwarding. Since many networks are partitioned into subnetworks and then connect to other networks for wide area communications, networks use specialized hosts called gateways or routers to forward packets between networks. Probably the most well-known network layer protocol is, of course, IP, or Internet Protocol. As I mentioned in the beginning of the course, the Internet Protocol, or IP, is responsible for addressing hosts, encapsulating data into packets, or datagrams, including fragmentation and reassembly, and routing packets from a source host to a destination host across one or more IP networks. So like other Layer 3 protocols, IP is connectionless, which means it doesn't care whether the packet has reached the destination or not. That's what Layer 4 is for. All right? So there are two versions of IP that currently coexist within the global Internet. IP version 4, or IPv4, and IP version 6, or IPv6. IP addresses are made up of binary values and drive the routing of all data over the Internet. IPv4 addresses are 32 bits long, and IPv6 addresses are 128 bits long. Right now we're going to see each of the versions in detail. But before we move on, let's compare the main features of each version. IPv4 is a 32-bit address, and IPv6 is a 128-bit address. Now, theoretically, you can address 2 to the power of 32 devices in IPv4, which is about 4.3 billion, right? In IPv6, on the other hand, you can address 2 to the power of 128 devices, which is, well, let's see. Why don't you just do the math on your own? So IPv4 is represented by the decimal equivalent of 4 octets, separated by dots. The biggest number one can make with 8 binary digits is 2 to the power of 8 minus 1, which means 255. So each octet can be any number from 0 to 255, right? Now, 128-bit IPv6 addresses are written using hexadecimal, as opposed to dotted decimal in IPv4. So because a hexadecimal number uses 4 bits, this means that an IPv6 address consists of 32 hexadecimal numbers. These numbers are grouped in 4s, giving 8 groups or blocks. The groups are written with a colon as a separator. Internet Protocol version 4, IPv4, is one of the core protocols of standards-based networking methods on the Internet. It was described in IETF publication RFC 791 in 1981, and it was the first version deployed for production in the ARPANET in 1983. It still routes most Internet traffic today despite the ongoing deployment of the successor protocol, IPv6. With IPv4, each address consists of 4 octets. Octet stands for 8-digit binary numbers. So an IPv4 address is 32 bits in total. So that means we can theoretically address 2 to the power of 32 devices with IPv4. So that means the address space of IPv4 is about 4.3 billion. Sounds like it's a big number, right? IPv4 is represented by the decimal equivalent of 4 octets separated by dots. The biggest number one can make with 8 binary digits is 2 to the power of 8 minus 1. That means 255. So each octet can be any number from 0 to 255. Now, also there are special meanings associated with two different ending numbers. In general, a last number of 0 stands for the network. Let's call that the base address. And a last number of 255 stands for all hosts on that network, called the broadcast address. Computers that are on the same local network share 3 of the 4 numbers. A computer can be on more than one network, so it can also have several names. So looking at an IP packet consisting of a header section and a data section, we'll see that the IPv4 packet header consists of 14 fields, and only the options field is, well, optional. Now, I'm not going to talk about each field one by one, but I'll give you a few short explanations of some of the more pertinent ones. The version field is always equal to 4. Why? IPv4. The Internet header length, IHL field, is the size of the header in words, where word is always going to be 32 bits. The total length is the entire packet size. In this case, it's in bytes. As you know, but to catch up to speed, 1 byte is 8 bits. The minimum size is 20 bytes, so that's a header without data, and the maximum is 65,535 bytes. The flag is used to determine the fragmentation options. Bit 1 is DF, or don't fragment. If it's set, and I mean by that if this bit is a 1, and fragmentation is required to route the packet, then the packet is dropped. Bit 2 is MF, or more fragment. For fragmented packets, all fragments except the last have the MF flag set. Bit 0 is reserved for the future. TTL, or time to live, is to limit the lifetime of a packet. It's a hop count, basically. When the packet arrives at a router, the router decrements the TTL field by 1. Protocol field is the protocol used in the data portion of the IP packet. So that's going to be TCP, UDP, ICMP. Source address and destination address fields are the most important fields of an IP header. These fields are the IPv4 address of the sender of the packet and the IPv4 address of the receiver of the packet. Please note that this address may be changed in transit by a network address translation device. We'll talk about that later. This is how an IPv4 packet is seen on Wireshark. So it's a DNS query response. The fields we mentioned are seen pretty clearly. Version is 4. Header length is 5 words, which means no options field. Total length is 96 bytes. MF and DF flags are not set. And you can see the source and the destination addresses and all the rest. I know what you're thinking. You're really chomping at the bit to get to subnetting, but before we talk about it, it's better to learn the IP classes and the subnet masks first, right? Octets of the IP address are broken down to provide an addressing scheme that can accommodate large and small networks. So there are basically 5 different classes of networks, and they range from A to E. We're going to focus on classes A, B, and C, which provide unicast addresses for networks of 3 different network sizes. Class D is for multicast networking, and the Class E address range is reserved for future or experimental purposes. So given an IP address, its class can be determined from the 3 high-order bits, and by that I mean the 3 leftmost bits in the first octet. In a Class A address, the first octet is the network portion. So Class A has a major network address of 1.0.0.0 all the way through 127.255.255.255. The next 24 bits are for the network manager to divide into subnets and hosts as he or she sees fit. Class A addresses are used for networks that have more than 65,536 hosts. In a Class B address, the first 2 octets are the network portion. So Class B has a major network address of 128.0.0.0 all the way through 191.255.255.255. Octets 3 and 4, that means 16 bits, are for local subnets and hosts. Class B addresses are used for networks that have between 256 and 65,534 hosts. And finally, in a Class C address, the first 3 octets are the network portion. Class C has a major network address of 192.0.0.0 all the way through 223.255.255.255. Octet 4, 8 bits, is for local subnets and hosts. Perfect for networks with less than 254 hosts. So a network masks helps you know which portion of the address identifies a network and which portion of the address identifies the node. An IPv4 subnet mask consists of 32 bits, a sequence of 1 followed by a block of 0. The trailing block of zeros designates that part as being the host identifier. Class A, B, and C networks have default masks, also known as natural masks, and these masks are 255.0.0.0 for Class A, 255.255.0.0 for Class B, and 255.255.255.0 for Class C networks. So an IP address for Class B network that has not been subnet would have an address mask pair similar to 131.107.1.2 being the address, and 255.255.0.0 would be the subnet mask, right? Now, in order to see how the mask helps you identify the network and node parts of the address, convert the address and mask into binary numbers as seen on the slide. So once you have the address and the mask represented in binary, then identification of the network and the host ID is a lot easier. Any address bits which have corresponding mask bits set to 1 represent the network ID. Any address bits that have corresponding mask bits set to 0 represent the host ID. So in this example, the first part, 131.107, is the network part of the IP address, where the rest, 1.2, represents the host. All devices on this segment share the same network ID and the same subnet mask. Now you can customize the subnet mask to divide a network into many smaller portions. So here's a little brain tingler for you. The network ID may be expressed in classless interdomain routing, or CIDR, notation, written as the first address of a network, followed by a slash character, and ending with a bit length of the prefix. So in our example, 131.107.0.0/16 is the prefix of the IPv4 network starting at the given address, having 16 bits allocated for the network prefix and the remaining 16 bits reserved for host addressing. Your patience pays off. Subnetting allows you to create multiple logical networks that exist within a single Class A, B, or C network. If you do not subnet, you are only able to use one network from your Class A, B, or C network, which is, well, pretty unrealistic. So subnetting is the process of designating some high-order bits from the host part as part of the network prefix and adjusting the subnet mask appropriately. So this divides a network into smaller subnets. In other words, in order to subnet a network, extend the natural mask with some of the high-order bits from the host ID portion of the address in order to create a subnetwork ID. So I'll give you an example. Let's take a Class C network of 192.168.2.0, which has a natural mask of 255.255.255.0. You can create subnets by moving 2 bits from the host part to the network prefix. Now, the last octet of the network mask starts with 11. So this 8-bit corresponds to 192 in decimal form. Now the network ID is 26-bit. In CIDR notation, it's now a /26 subnetwork. You can find the network prefix by a bitwise AND operation between the IP address and the subnet mask. The number of subnetworks available and the number of possible hosts in a network may be readily calculated. In our example, 2 bits were borrowed to create subnetworks, thus creating 2 to the power of 2 possible subnets. You with me? So now let's calculate the maximum number of hosts for each subnet. In our example, 26 bits are used to define the network. The remaining bits after the subnet bits are used for addressing hosts within the subnet. So, the host part of the IP address is 6-bit. All zeros and the all ones values for the host ID are not allowed in a subnetwork, right? These 2 values are reserved for the network address and broadcast address, respectively. So the maximum number of hosts which can be addressed in these subnetworks is 2 to the power of 6 minus 2, which equals 62. Excellent. So as a result, the IP addresses of the devices in the subnetwork 192.168.2.128/26 will be between 192.168.2.129 and 192.168.2.190. So, as I mentioned before, the IPv4 address is a 32-bit number, which allows us to address maximum of 2 to the power of 32 devices in theory. That means there are fewer than 4.3 billion addresses available. See where I'm going with this? It's a problem because there are many more than 4 billion internet-connected devices in the world. Desktop and laptop computers, smartphones, smart TVs, smart cars, even smart fridges, smart ovens, the Internet of Things. It's the future, baby. This has led to a shortage of IPv4 addresses. So, my friend and fellow genius, what is the solution to the problem? I think the long-term solution is to switch to Internet Protocol version 6, IPv6. IPv6 has trillions of addresses, enough to give every computer in the world a unique IP address. We'll get to that detail very soon. But the most important effort to migrate the IPv4 shortage is using Network Address Translation, NAT, which allows a private network to use one public IP address, and that permits lots of private addresses in the private network. But wait a second, wait. Private network, NAT? What the heck are you talking about now? I thought you wanted to go to IPv6. Let me explain. Up to now, all the networks that we mentioned were assumed to be a public network, and all of the IP addresses were public IP addresses, right? In the Internet addressing architecture, a private network is a network that uses private IP address space. Wait. I'll try to explain an unknown with another one. But first, I should explain what the private IP address space is. Tell you what, let's take a break here, and I'll talk about the special use IP addresses, including the private IP address space. So, the authorities, IETF and IANA, please don't ask. You can Google it if you really want to know who they are. But they've restricted from general use various reserved IP addresses for special purposes. So that means you cannot use any IP address in these reserved blocks as the public IP addresses of your devices. So here we have some of these reserved blocks. Now, these are the most important blocks for us to know, because pretty much anybody who's not familiar with the networking concept gets confused about the difference between public and private IP addresses. So these IP blocks are reserved for private networks. They're commonly used for home, office, and enterprise local area networks, or LANs. Private IP address spaces were originally defined in an effort to delay IPv4 address exhaustion, but they're also a feature of IPv6, where exhaustion is not an issue. Bear with me. Packets addresses in these ranges are not routable in the public internet because they are ignored by all public routers. Therefore, private hosts cannot directly communicate with public networks, but require Network Address Translation, or NAT, at a routing gateway for this purpose. But no worries, we'll talk about NAT coming up next. So without getting too deep, the only thing about the loopback is that 127.0.0.1 is the most common IPv4 address which is mapped to the local host. So let me give you an example. The IP address of your host machine is 172.16.99.222, and a web application is served in your host. Now, in that machine, you can use the web address hhp://127.0.0.1 to access the web app, as well as hhp://172.16.99.222. Both IP addresses point to the same machine, which is your host. Generally, an IP address that starts with 169 means that your computer wasn't able to obtain an IP address from your DHCP server. Usually that means that your router is wedged and needs to be rebooted, or that your Wi-Fi isn't working at all. So now let's have a look at the private IP address blocks closely. As I mentioned a few minutes ago, a private network is a network that uses private IP address space. Administrators of private networks can assign networks and subnets from the above ranges. If an administrator decides to use the IP range 192.168.0.0/16 and then decides to have a single subnetwork assigning 255.255.0.0 as a subnet mask, then he or she will have a subnet with a max of 65,536 devices. Make sense? Okay. I know there are a lot of terms and conditions, so let's just break it down with a real-world scenario. Although the standard for A and B class networks specify 8 and 16-bit masks respectively, it's common to assign non-standard masks for subnets, resulting in much more limited address spaces. Right? For example, using 10.xx.yy.0/24 results in 256 host company subnets, right? So this is done for scalability and, of course, security. Okay, so we're the system administrators in Company X and ready to build. We have decided to use 192.168.x.x as the private IP address space for our company. If we use the natural mask 255.255.0.0, that means we use the first 16 bits for network ID, and we'll have a single network. So in this case, we can address 65,536 devices in this network. Well, of course, the first IP and the last IP we're not allowed to use, so the number of IP addresses is actually 65,536 minus 2. You do the math. But in practice, for ease of use, it's pretty much used as the power of 2. So you can use an IP address in this network from 192.168.0.1 to 192.168.255.254. But we need to have different networks. One for the managers, one for the developers, one for the servers, etc. So, for the sake of our use and our sanity, let's use the next 8 bits for subnets. In this case, we have a subnet mask of 255.255.255.0. 8 bits for subnets, and 24 bits for the network ID in total. 8 bits left for addressing the devices under the subnets. So as a result, we can create 256 subnets and address 256 devices for each one. Now we have 256 address ranges for 256 subnetworks. So the table here shows a few examples of our potential subnetworks. The red colored blocks are added to the network ID as subnet identifiers. The rest of the 8 bits are used as the host IDs. In the 4-block decimal notation, the third block identifies the subnetwork, and the last block identifies the host. So, breaking it down, it's much simpler now, isn't it? Excellent. Let's move on. So the private addressing scheme works really well for computers that only have to access resources inside the network, like workstations needing access to file servers and printers and so forth. Routers inside the private network can route traffic between private addresses with no trouble whatsoever. However, to access resources outside the network, like the internet for example, these computers need to have a public address so that responses to their requests return to them. Now this is where NAT comes into play. A workstation inside a private network makes a request to a computer on the internet. The switches or the routers within the network recognize that the request is not for a resource inside the network. So they send the request to the router, let's say the backbone router. Now, the backbone router sees the request from the computer with the internal IP. It then makes the same request to the Internet using its own public address and returns a response from the Internet resource to the computer inside the private network. From the perspective of the resource on the Internet, it's sending information to the address of the router. From the perspective of the workstation, it appears that the communication is directly with the site on the Internet. So when NAT is used like this, all users inside the private network that access the Internet have the same public IP address. So that means only one public address is needed for hundreds or even thousands of users. So let's have a look and see how it works. Here's a typical home network. There's a laptop, desktop PC, and a smartphone, all connected to our home router. And the home router is, of course, connected to the Internet. So when we register with our ISP, the Internet Service Provider, we get an IP address that is accessible throughout the Internet, and that's pretty much assigned to that home router. We refer to it as real IP or public IP. Now suppose that the IP address 20.20.20.20 is assigned to our home router. Our devices inside the home network also have IP addresses, right? But in this case, they get private IP addresses which are assigned by the home router and are not accessible from the Internet. So as you can see here, the public IP addresses are red and the private IP addresses are green. So let's consider a connection request from the smartphone which requests the homepage of abc.com. So to reach the page, the smartphone has to go through the home router. The packet has the source IP address and the source port address, as well as the destination IP address and the destination port. If it arrives at the web server with these values, it processes the request and tries to send the reply packet to the IP address 192.168.1.5. But that's unreachable for the web server because it's a private IP address. So, when the packet arrives at the home router, instead of sending the packet right over the Internet, the home router changes the source IP address with its very own public IP address. It also creates a record in the NAT forwarding table. This table allows us to know which packets will be redirected to the smartphone when they come in. So moving right along, the packet travels over the Internet and arrives at the web server. The web server creates a reply packet where the source IP address is itself and the destination IP address is the public IP address of the home router. When our home router receives a response, it looks at the NAT forwarding table and replaces the destination IP and the port according to the mapping inside the table. And finally, the smartphone receives the packet. Pretty cool, huh? IPv6 was developed by the Internet Engineering Task Force, IETF, I'm sure you looked it up, to deal with the long-anticipated problem of IPv4 address exhaustion. So IPv6 is intended to replace IPv4. IPv6 became a draft standard in December 1998 and became an Internet standard on the 14th of July, 2017. So instead of 32-bit addressing of IPv4, which provides approximately 4.3 billion addresses, IPv6 uses a 128-bit address. So that theoretically gives us 2 to the power of 128, or approximately 3.4 times 10 to the 38th addresses. Big number. You can check my math later, but stick with me for now. I mean, the actual number is slightly smaller, as multiple ranges are reserved for special use, or they're just completely excluded from use. But with a rough calculation, the total number of possible IPv6 addresses is more than 7.9 times 10 to the power of 28 times as many as IPv4. The two protocols, IPv4 and IPv6, are not designed to be interoperable, complicating the transition to IPv6. However, several IPv6 transition mechanisms have been devised to permit communication between IPv4 and IPv6 hosts. In addition to offering more addresses, IPv6 also implements features not present in IPv4. Simplified header, IPv6's header has been simplified by moving all unnecessary information and options, which are present in the IPv4 header, to the end of the IPv6 header. The IPv6 header is only twice as big as an IPv4 header because that IPv6 address is 4 times longer. End-to-end connectivity. Every system now has a unique IP address and can traverse through the Internet without using NAT or other translating components. After IPv6 is fully implemented, every host can directly reach other hosts on the Internet with some limitations involved, like a firewall, organization policies, and stuff like that. Auto-configuration. IPv6 supports both stateful and stateless auto-configuration mode of its host devices. This way, the absence of a DHCP server does not put a halt on inter-segment communication. Faster forwarding and routing. A simplified header puts all unnecessary information at the end of the header, like we saw earlier. The information contained in the first part of the header is adequate for a router to make its routing decisions, thus making them as quickly as looking at the mandatory header. IPsec. Initially, it was decided that IPv6 must have IPsec, making it more secure than IPv4. This feature has now been made optional. IPsec, Internet Protocol Security, is a framework of open standards for helping to ensure private, secure communications over Internet Protocol networks, IP networks, through the use of cryptographic security services. IPsec is an end-to-end security scheme operating in the network layer. While some Internet security systems in widespread use, TLS and SSH, operate in the upper layers, IPsec can automatically secure applications at the IP layer. No broadcast. Though Ethernet and Token Ring are considered a broadcast network because they support broadcasting, IPv6 does not have broadcast support anymore. It uses multicast to communicate with multiple hosts. Mobility. IPv6 was designed keeping mobility in mind. This feature enables hosts, such as a mobile phone, to roam around in different geographical areas and remain connected with the same IP address. The mobility feature of IPv6 takes advantage of auto IP configuration and extension headers. Extensibility. One of the major advantages of the IPv6 header is that it is extensible, adding more information in the option part. IPv4 provides only 40 bytes for options, whereas options in IPv6 can be as much as the size of the IPv6 packet itself. What is the IPv6 packet, you ask? You came to the right place. An IPv6 packet is the smallest message entity exchanged via the Internet Protocol across an IPv6 network. But stay with me here. The packets consist of control information for addressing and routing, and a payload consisting of user data. The control information in IPv6 packets is subdivided into a mandatory fixed header and optional extension headers. The fixed header starts an IPv6 packet and has a size of 40 octets, which means 320 bits. Its format is shown in the slide. Version is constant 6. Payload length is the size of the payload in bytes, including any extension headers. Hop limit replaces the time to live field in the IPv4. Well, I think source address and destination address fields are fairly obvious. Extension headers carry optional Internet layer information and are placed between the fixed header and the upper layer protocol header. 128-bit IPv6 addresses are written using hexadecimal, as opposed to dotted decimal back in IPv4. Because a hexadecimal number uses 4 bits, this means that an IPv6 address consists of 32 hexadecimal numbers. These numbers are grouped in 4s, giving 8 groups or blocks. The groups are written with a colon as a separator. An IPv6 address example is shown in the slide. So because of the length of the IPv6 addresses, various shortening techniques are employed. The main technique being to omit repetitive zeros, as shown in the example. So as I mentioned before, in IPv4, an address is split into 2 components, right? A network ID and a host ID. This was done initially using address classes and then later using subnet masking. In the unicast addressing of IPv6, it's done in the same way. The first step is to split the address into two parts. The address is split into two 64-bit segments. The top 64 bits is a network ID, and the lower 64 bits is the host ID. The most significant 64 bits are used for routing, and the least significant 64 bits identify the address of the interface or host. This block is derived from the actual physical or MAC address in practice. So if we look at the most significant 64 bits in more detail, we can see that it's split into two blocks of 48 and 16 bits. Now, the least significant 16 bits are used for subnets on internal networks and are controlled by a network administrator. The most significant 48 bits are used for the global network addresses and are used for routing over the Internet. Dynamic Host Configuration Protocol, DHCP. Now, it's a protocol used to provide automatic and central management for the distribution of IP addresses within a network. It's also used to configure the proper subnet mask, default gateway, and DNS server information on the device. In most homes and small businesses, the router acts as the DHCP server. In large networks, a single computer might act as a DHCP server. In short, the process goes like this. A device, the client, requests an IP address from a router, the host, after which the host assigns an available IP address to allow the client to communicate on the network. So let's look at some of the advantages of using DHCP. A computer or any other device that connects to a network, local or internet, must be properly configured to communicate on that network. Makes sense? Since DHCP allows that configuration to happen automatically, it's used in almost every device that connects to a network, including computers, switches, smartphones, gaming consoles, you name it. Now, because of this dynamic IP address assignment, there's less of a chance that two devices will have the same IP address, which is very easy to run into when using manually assigned static IP addresses. Using DHCP also makes a network much easier to manage. From an administrative point of view, every device on the network can get an IP address with nothing more than their default network settings, which is set up to obtain an address automatically. So that's easy, gives them nothing to call the help desk about. The only other alternative is to manually assign addresses to each and every device on the network. You're not getting paid enough to do that. So because these devices can get an IP address automatically, they can move freely from one network to another, given that they're all set up with DHCP, and receive an IP address automatically, which is super helpful with mobile devices. Now, as a cybersecurity expert, you should know one more thing about the DHCP mechanism. The first device which replies to a DHCP discover request decides the configuration of the client. There is not any mechanism to authenticate the DHCP server. Similarly, a DHCP server tries to reply to all the DHCP requests, and again, there is no authentication mechanism for the clients who request an IP. You get it? I think you do. What if a hacker replies before the real DHCP? Or what if a client sends a lot of DHCP discovery requests by changing the MAC address each time? So let's have a look to see how a DHCP mechanism works in detail. Once a device is turned on and connected to a network that has a DHCP server, it will send a request to the server called a DHCP discover request. After the discover packet reaches the DHCP server, the server attempts to hold on to an IP address that the device can use and then offers a client the address with a DHCP offer packet. Once the offer has been made for the chosen IP address, the device responds to the DHCP server with a DHCP request packet to accept it. After which, the server sends an ACK packet that's used to confirm that the device has that specific IP address and to define the amount of time that the device can use the address before getting a new one. If the server decides that the device cannot have the IP address, it will send a NAC. Let's see the DHCP server mechanism in Wireshark. So Wireshark is already embedded into Kali, and it's ready to use. In addition, I'd also like to show you how to download and install it in a Windows system. So right now I'm in a Windows 8 system. Open the internet browser and search for Wireshark for Windows, using those as the keywords. First link is the download page of wireshark.org. So let's click it. My Windows is 64-bit, so I'll download the 64-bit, which is the latest stable version. Click it and save the installer. Now, it takes less than a minute, unless your connection is a mess. You might want to look into that. Just kidding. Click to run it. The setup wizard opens. Okay, so simply it's a next, finish installation. No need to change anything. Wait until the installation finishes. Okay, so check this to run Wireshark now and click Finish. And welcome to the Wireshark and Windows interface. So now I will show you the DHCP mechanism in Wireshark. So let's run Wireshark, and you can see that it's listing the packets received by ETH0. So to demonstrate the DHCP mechanism, we need to ask for an IP address over at the DHCP server. From the bottom right corner, right-click to the network icon and select Open Network and Sharing Center. Click Ethernet 0 and then Properties. You'll have to scroll down a little bit and double-click IP version 4. And as you see here, the IP address is manually set for my Windows 8. So to start a DHCP request, I'll choose Obtain an IP address and DNS server address automatically. Those are my options. Now, before I click OK, I'll go to Wireshark and restart capturing by clicking the green button on the toolbar. So now Wireshark Windows will be cleaned. Continue without saving. So now go to the network status window and click OK. And we can close all the networking windows. So Wireshark captured the packets. Well, it's still capturing, but let's go to the top of the list to find the DHCP packets. So here the DHCP Discover packet is right here at the top of the list. When we look at the ports in the UDP header, we see that the port 68 is used to send DHCP Discover packets. So let's go back to the filter box and type UDP port equals 68, and now we have the DHCP packets only. So the first packet is DHCP Discover. And as I mentioned before, it's broadcast. Source IP is all zeros because we don't have an IP address at the moment. Destination IP is all ones, 255.255.255.255 because it's a broadcast packet. And right here is Bootstrap Protocol, which is an application layer protocol used by DHCP mechanisms. The second packet is a DHCP offer packet sent by the DHCP server, 172.16.99.254 to the Windows system. The destination IP is 172.16.99.233, which is offered to the DHCP server. So in here, the destination MAC address is important. That's what's going to be targeted according to the MAC address. So as you see, the destination MAC address of the DHCP offer packet is the same as the source MAC address of the DHCP Discover packet. Now the third packet is the DHCP request sent by the Windows system. It's still a broadcast packet and the source IP is still all zeros. The message is request and the requested IP address is an option 50. So if you expand it, you see the requested IP address. And it's the same as the offered IP address, 172.16.99.223. The last packet is DHCP-ACK, sent by the DHCP server to the Windows system. This packet completes the DHCP mechanism successfully. So from now on, the IP address of our Windows system is 172.16.99.223. Internet Control Message Protocol, ICMP, is an error reporting protocol that network devices like routers use to generate error messages to the source IP address when network problems prevent delivery of IP packets. ICMP messages are sent in several situations. For example, when a datagram cannot reach its destination, when the gateway does not have the buffering capacity to forward a datagram, and when the gateway can direct the host to send traffic on a shorter route. The Internet protocol is not designed to be absolutely reliable. I'll explain why. Hold on. The purpose of these control messages is to provide feedback about problems in the communication environment, not to make IP reliable. There's still no guarantees that a datagram will be delivered or a control message will be returned. Some datagrams may still be undelivered without any report of their loss. The higher-level protocols that use IP must implement their own reliability procedures if reliable communication is required. So the ICMP header starts after the IPv4 header. All ICMP packets have an 8-byte header and variable-size data section. The first 4 bytes of the header have a fixed format, while the last 4 bytes depend on the type and code of that ICMP packet. ICMP type and code in the header identifies the control message. Some of the ICMP control messages are shown in this slide. So ping is the most well-known application of the ICMP. It operates by sending ICMP echo request packets to the target host and then waiting for an ICMP echo reply. Some routers and firewalls are configured to not pass ICMP echo requests or echo reply requests. Attackers sometimes try to map out remote networks by pinging all the possible addresses and collecting replies, so blocking this type of traffic at the perimeter is fairly common. Just because you do not receive a reply to a ping does not necessarily mean that the host is not available. Traceroute is a computer network diagnostic tool for displaying the route or path of packets through the Internet between your computer and a specified destination computer. It also measures the amount of time each hop took. When you run the utility, it initiates the sending of a packet, including in the packet a TTL, a time-to-live value, which is also known as a hop limit. As the packet passes through a router, the TTL is decremented until, when the TTL reaches 0, the packet is destroyed and an ICMP time-exceeded message is returned. Traceroute works by setting the TTL for a packet to 1, sending it towards the requested destination host, and listening for the reply. When the initiation machine receives a time-exceeded response, it examines the packet to determine where the packet came from, so this identifies the machine 1 hop away. Then the tracing machine generates a new packet with TTL 2 and uses that response to determine the machine 2 hops away, and so on. The command traceroute is available on many modern operating systems. On Unix-like systems such as FreeBSD, macOS, and Linux, it's available as a command line tool. On Unix-like systems, traceroute sends, by default, a sequence of UDP packets. Traceroute is also graphically accessible in macOS within the Network Utility Suite. In Microsoft Windows, it's named Tracert. In Windows, Traceroute sends ICMP echo requests instead of UDP packets. For IPv6, the tool sometimes has a name Traceroute 6 or Tracert 6. Let's look how the traceroute command operates in our host machine and virtual machines as well. So I'm on my host machine, this is Mac OS, and I'll open a terminal screen, Command Space to open the Spotlight search bar, and type terminal. Start the terminal app, and now I'm on a terminal screen. Traceroute is the command I'll use. So if you run it with no parameter, you get a brief help about the usage of the command. So now let's run the command with a target host. We timed out in the first hop. And in the second one as well. Well, it happens, no worries. And yes, here are the other hops. This is the path that the packets follow from my host machine to the target web server. In Mac OS, you can also trace the packets with a graphical UI, which I mentioned before. So go to the Network Utility tool, Press Command and Spacebar once more to open Spotlight and type Network Utility and find it and open it. There's a Traceroute tab in the Network Utility window. Just type the target host and click the Trace button. Let's see how it all works in Kali. So now I'm in Kali, and I have a terminal screen open. Type Traceroute and hit Enter. So you'll see the help for this particular command, and it's a bit more detailed than the one in macOS. So now I want to show you the network configuration of my Kali. Go to Kali Settings, click Network Adapter, and as you see, we run Kali in NAT mode, where the host machine, Mac, provides network address resolution, we'll talk about that soon, for all network traffic, and Kali shares the IP address of the host. Now I want to test the network connection first. So I'll ping the Google DNS 8.8.8.8, and right, that's no problem at all. You can use Control-C keys to end the ping command. Just don't use Control-L. Okay, now I'll run the trace route with the target host in Kali. The first hop is a gateway prepared by VMware for my virtual machines, and as you can see, all the other hops are blocked. We cannot trace packets from the VM in NAT mode. So let's have a look at the traceroute command options once more. Here there's an option, uppercase T, which sends TCP SYN packets. Now I'd like to try the command once more with this option. Okay, so we have the first and the last hop this time. So now I want to show you the command in a Windows system. Here is my up-to-date Windows 8 system. It has an IP. Check the connection, ping, and yes, the network is running. Good, just where we want it. Let's look at the network details first. From the Network and Sharing Center, click Ethernet 0, and then the Details button, and here are the details. Default gateway is 99.2, DHCP is 99.254, as you know. These are the devices prepared by VMware for our NAT network. So now I go to the settings of the VMware Fusion. In Network Adapter, we confirm that the VM is in NAT network mode. Now I'm in the command prompt. As I mentioned, the command is tracert in Microsoft systems. So write down the target host and press Enter. So the first hop is, again, the gateway. And just like in Kali, since this VM is also in NAT mode, the requests for other hops are timed out. So while the command is running, I'd like to show you the command help. So just type tracert and hit Enter. So we didn't enter the host this time, and here's a usage of the tracert command. Trace completed, and there is no result given. As expected, because we're in NAT mode. I know you knew that, but I just wanted to make sure. So, now I'm going to run my Windows VM in bridge mode and try the command once more. And once again, click the hardware settings icon on the menu bar of VMware Fusion and select Network Adapter. So I'm using Wi-Fi to connect to the internet right now, so I choose Wi-Fi under the bridged networking section. Now this is the IP address assigned by the DHCP, and the subnet mask of the network, again, is set by DHCP. So we'll see how the DHCP works. Just stay with me here. So as you see in the Network and Sharing Center window, the active network disappeared as soon as I changed the network adapter of the VM. In a second, the new network is activated. Click Ethernet 0 and look at that, the Details button. So click on that to see the network settings, and those are the new ones. So now we're in the 192.168.12.x IP block. And we have a different DHCP and gateway run by the network admins of my office building. So let's go back to the command prompt and trace the route of the packets once more. So first I want to check the network, as I always do. So I'll ping the Google DNS, and yes, we have the internet connection. So now is the time to trace the route. The first request is timed out. Remember, the results of my host machine, right? The second request timed out as well. And here are the other hops. We now have the results. So now we're in the fourth layer of the OSI reference model, the transport layer. Welcome to the layer of TCP. The transport layer is the level at which system reliability and quality are ensured. The basic function of the transport layer is to accept data from the layer above, split it up into smaller units, pass these data units to the network layer, and ensure that all the pieces arrive correctly at the other end. Okay, so now let's look at the functions of the transport layer in detail. Service point addressing. Transport layer header includes service point address, which is the port address. This layer gets the message to the correct process on the computer, unlike network layer, which gets each packet to the correct computer. Segmentation and reassembling. A message is divided into segments. Now each segment contains a sequence number, which enables this layer to reassemble the message. The message is reassembled correctly upon arrival at the destination and replaces packets which were lost in transmission. Connection control. It includes two types. Connectionless transport layer. Each segment is considered as an independent packet and delivered to the transport layer at the destination machine. Connection-oriented transport layer. Before delivering packets, connection is made with the transport layer at the destination machine. Flow control. In this layer, flow control is performed end-to-end. The rate of data transmission between two nodes must sometimes be managed to prevent a fast sender from transmitting more data than can be supported by the receiving data buffer, causing a buffer overrun, and we don't want that. Error control. Error control is performed end-to-end in this layer to ensure that the complete message arrives at the receiving transport layer without any error. Error correction is done through retransmission. On the Internet, TCP and UDP provide the services for most applications. Coming up next, we'll look at all the other details of the transport layer under TCP and UDP topics. The Transmission Control Protocol, TCP, provides a communication service at an intermediate level between an application program and the Internet protocol. It provides host-to-host connectivity at the transport layer of the Internet model. TCP works with the Internet Protocol, IP, which defines how computers send packets of data to each other. Together, TCP and IP are basic rules defining the Internet. TCP is a connection-oriented protocol, which means a connection is established and maintained until the application programs at each end have finished exchanging messages. It determines how to fragment application data into packets that networks can deliver, sends packets to and accepts packets from the network layer, manages flow control, and, because it is meant to provide error-free data transmission, handles retransmission of dropped or garbled packets, as well as acknowledgement of all packets that arrive. Let's see the connection-oriented error-free communication of TCP in an example. When a web server sends an HTML file to a client, it uses the HTTP protocol to do so. The HTTP program layer asks the TCP layer to set up the connection and send the file. The TCP stack divides the file into packets, numbers them, and then forwards them individually to the IP layer for delivery. Although each packet in the transmission will have the same source and destination IP addresses, packets may be sent along multiple routes. The TCP program layer in the client computer waits until all of the packets have arrived, then acknowledges those it receives and asks for the retransmission on any it does not, based on missing packet numbers. Then assembles them into a file and delivers the file to the receiving application. The TCP three-way handshake is the method used by TCP to set up a connection. TCP's three-way handshaking technique is often referred to as SYN, SYNAC, ACK, because there are three messages transmitted by TCP to negotiate and start a TCP session between two computers. This three-way handshake process is also designed so that both ends can initiate and negotiate separate TCP socket connections at the same time. That means the connection is full duplex. Oh, you know what? We have to take a break at this point and talk about TCP flags. There are 1-bit flags in TCP headers, which are called TCP flags. TCP flags are used within TCP packet transfers to indicate a particular connection state or provide additional information. Ignoring ECE, CWR, and NS flags for now, there are basically 6 TCP flags. The SYN, or synchronization flag, is used as a first step in establishing a three-way handshake between two hosts. Only the first packet from both the sender and the receiver should have this flag set. The ACK flag, which stands for acknowledgement, is used to acknowledge the successful receipt of a packet. The RIST flag, which stands for reset, gets sent from receiver to the sender when a packet is sent to a particular host that was not expecting it. The FIN flag, which stands for finished, means there is no more data from the sender. Therefore, it is used in the last packet sent from the sender. The PSH flag, which stands for push, is somewhat similar to the URG flag and tells the receiver to process these packets as they are received instead of buffering them. The URG flag is used to notify the receiver to process the urgent packets before processing all other packets. So every legitimate TCP connection begins with a TCP three-way handshake, which is used to exchange sequence numbers so that lost packets can be retransmitted and packets can be placed in the proper order. If machine A wants to initiate a connection to machine B, it will start by sending a TCP packet with a SYN control bit set. This packet will include an initial sequence number, which I'll call here ISNA, because it comes from machine A, which is 32 bits long and typically generated in a pseudo-random fashion by the TCP software on machine A. The ACK number, another 32 bits in the TCP header, is typically set to 0 because it is ignored in this initial SYN. Some operating system variants may make this ACK number non-zero, but either way, it's ignored by the destination machine. So if the destination port is open, that is, there is something listening on that port, it must respond with a SYN ACK packet back, a packet that has both the SYN and ACK control bits set at the same time. This packet will have a sequence number of ISNB, a pseudo-random number assigned by machine B for this connection. The SYN ACK packet will have an acknowledgement number of ISNA plus 1, indicating that machine B has acknowledged the SYN packet from machine A. To complete the three-way handshake, machine A responds with an ACK packet which has a sequence number of ISNA plus 1. It's the next packet, so the sequence number has to change from the value in the original SYN packet. The acknowledgement number field is set to ISNB plus 1, thereby acknowledging the SYN ACK packet, right? So we have now exchanged sequence numbers. All packets going from A to B will have increasing sequence numbers starting at ISNA plus 1, going up by a value of 1 for each byte of data transmitted in the payloads of A to B packets. Likewise, all responses back from B will have sequence numbers starting at ISNB plus 1 and going up for each byte of data from B to A. In essence, we have two streams of sequence numbers in this series of packets, one from A to B, originally based on ISNA, and the other from B to A, originally based on ISNB. Perfect. A TCP segment consists of a segment header and a data section. The TCP header contains 10 mandatory fields and an optional extension field. The optional field is the options field, which is the last field seen on the slide. The TCP header includes a source port and destination port, each 16 bits in length. The source port is the port on the originating machine that emitted the packet. The destination port indicates the port on the target machine the packet should be delivered to. The sequence number and an acknowledgement number allows TCP to track a series of packets to make sure they arrive reliably and pretty much in order. No, absolutely in order. If a packet is lost, TCP will retransmit it. If packets arrive out of order, TCP will adjust them to make sure that they are delivered to the destination services in the proper order. Data offset specifies the size of the TCP header in 32-bit words. The minimum size header is 5 words, and the maximum is 15 words. There is also TCP control bit space, also known as flags, which are incredibly important for tracking the state of a given TCP connection. As you know, we talked about them a few minutes ago. Of course, if you didn't take a break, it was a few minutes ago. But whatever you do, just don't spill on the keyboard. Now, TCP senders use a number called window size, which is in bytes by default, to regulate how much data they send to a receiver before requiring an acknowledgement in return. So if the window size becomes too small, network data transfer will be unnecessarily slow, while if the window size becomes too large, the network link can become saturated or the receiver may not be able to process incoming data quickly enough, also resulting in slow performance. Windowing algorithms built into the protocol dynamically calculate size values and use this field of the TCP headers to coordinate changes between senders and receivers. A full duplex communication is established. UDP is another protocol of transport layer, layer 4, used primarily for establishing low latency and loss-tolerating connections between applications on the Internet. TCP has emerged as the dominant protocol used for the bulk of Internet connectivity, owing to its services for breaking large data sets into individual packets, checking for and resending lost packets, and reassembling packets into the correct sequence. But these additional services come at a cost in terms of additional data overhead and delays called latency. In contrast, UDP just sends the packets, which means that it has a much lower bandwidth overhead and latency. But packets can be lost or received out of order as a result, owing to the different paths individual packets traverse between sender and receiver. So UDP uses a simple connectionless communication model with a minimum of protocol mechanism. It has no handshaking dialogues and thus exposes the user's program to any unreliability of the underlying network. There is no guarantee of delivery, ordering, or duplicate protection. UDP is suitable for purposes where error checking and correction are either not necessary or are performed in the application. UDP is an ideal protocol for network applications in which perceived latency is critical, such as gaming, voice, and video communications, which can suffer some data loss without adversely affecting perceived quality. In addition, since it's transaction-oriented, suitable for simple query response protocols such as the domain name system or the network time protocol. The UDP header is pretty simple. It consists of 4 fields, each of which is 2 bytes, 16 bits. The use of the fields checksum and source port is optional in IPv4. Are you surprised to hear that the source port is optional? But don't be, because, as you know, a UDP packet does not expect to get a reply in general. And again, since UDP doesn't care about the errors, the checksum field is, again, optional. Source port identifies the sender's port, and the destination port identifies the receiver's port as well. And the length field specifies the length of the UDP header and data in bytes. So now's a good time to compare the two protocols, UDP and TCP, as a brief summary. Most services on the Internet use either TCP or UDP, which are carried end-to-end across the network using IP, either IPv4 or IPv6. The Transmission Control Protocol, TCP, and User Datagram Protocol, UDP, are very different. TCP is a connection-oriented protocol which tries to ensure reliable, in-order delivery of packets. If packets are lost, TCP automatically retransmits them. If they arrive out of order, TCP will resequence them before handing them up to an application. UDP is connectionless. The UDP software makes no attempt to associate streams of packets together, So as far as UDP is concerned, each packet is completely independent, unrelated to other packets. No attempt is made by UDP for retransmission or resequencing. If a packet is lost via UDP, it's up to the higher layer application to resend it. And finally, we're in the application layer. Now, if you remember, I mentioned before, for the ease of use, the last three layers, session layer, presentation layer, and application layer, are thought of together as the application layer. As you know, these three layers are already a single layer in the TCP/IP reference model. So the application layer contains the communications protocols and interface methods used in process-to-process communications across an Internet Protocol computer network. The application layer only standardizes communication and depends upon the underlying transport layer protocols to establish host-to-host data transfer channels and manage the data exchange in a client-server or peer-to-peer networking model. So let's have a look at some important protocols of the application layer. The often used analogy to explain the domain name system is that it serves as the phone book for the Internet by translating human-friendly computer host names into IP addresses. Simply, DNS is a directory of names that match with IP addresses. As you may know, each device connected to the Internet has a unique IP address which other machines use to find the device. DNS servers eliminate the need for humans to memorize IP addresses, such as 212.80.75.134. Think about the websites you visit every day, Google and YouTube, Facebook, Twitter, etc. Without DNS, we would have to reach these sites by using their IP addresses instead of their names. I think remembering the names is so much easier than remembering the strange numbers. But it's still possible to reach the computer with that strange number string as well. Now, DNS deserves to have far more time spent on it. It could be a whole course in and of itself. Special protocols. DNS is a client-server network communication system. DNS clients send their requests to and receive the responses from DNS servers. The requests containing the name and resulting in an IP address being returned from the server are called forward DNS lookups. The requests containing IP addresses and resulting in the names are called the reverse DNS lookups. The DNS directory that matches name to number isn't located all in one place. Pretty much like the Internet itself, the directory is distributed around the world, stored on domain name servers that all communicate with each other on a very regular basis to provide updates as well as redundancies. With more than 332 million domain names listed by the end of 2017, a single directory would be very large indeed. So when you type mail.google.com into your browser sends a query over the Internet to find the website. It's a query seeking to match the domain name with its corresponding IP address. So let's follow the path of this question over the Internet infrastructure. The first server your query interacts with is the DNS resolver, which can be operated by your ISP, Internet Service Provider. A resolver is basically responsible for initiating and sequencing the queries that ultimately lead to a full resolution. Domain name resolvers determine the domain name servers responsible for the domain name in question by a sequence of queries, starting with the rightmost, in other words, top-level domain label. Assuming the resolver has no cached records to accelerate the process, which is the worst-case scenario, the resolution process starts with a query to one of the root servers. The root servers are running all over the world, and each one knows DNS information about top-level domains, or TLD, such as .com. So to begin answering your query, the resolver asks a root server for DNS information about .com. So there are 13 sets of root servers in more than 300 locations around the world. Each TLD DNS name server stores the address information for second-level domains within the top-level domain, .com in our example. The second-level domain is google.com. When your query reaches the TLD server answers with the IP address of the domain's name server, which will provide the next piece of the puzzle. So this is the final step of address resolution. The recursive resolver sends the query to the domain's name server. This DNS server knows the IP address for the full domain, mail.google.com, and that answer is returned to the recursive resolver. Now that the recursive resolver knows the IP address for the domain name in your query, the recursive resolver tells the browser what the IP address is. So finally, your browser can send a request to the website to retrieve the website's content, using the IP address it just learned. This whole process might seem, well, complicated. It certainly sounds it to talk it out, but really takes very little time at all. Hypertext Transfer Protocol, HTTP, is an application protocol. Hypertext is basically structured text that uses logical links between nodes containing text. And HTTP is the protocol to exchange or transfer hypertext. So HTTP is a stateless protocol. That means no information is retained by either sender or receiver. It functions as a request-response protocol in the client-server computing model. A web browser, for example, may be the client, and an application running on a computer that's hosting a website may be the server. The client submits an HTTP request message to the server. The server, which provides resources such as HTML files and other content, returns a message to the client. The response contains completion status information about the request and may also contain requested content in its message body. So the most used HTTP request is GET. A GET request is designed to request server resources. With this type of request, the parameters are sent to the server inside the URL. A POST request is designed to request server resources as well as a GET request. Unlike a GET request, parameters are sent to the server inside the body of the request instead of the URL. Well, it's still possible to send the parameters inside the URL, but if you use a POST request, it's better to send parameters inside the body than inside the URL. So what's the advantage of sending parameters inside the body instead of the URL? Almost always, the traffic between the server and the client is logged on the server side. Such log files usually contain the URL. If you send the parameters in the URL, they are saved as clear text in your log files. So anyone who can see the log files can also see your sensitive parameters. You should use POST requests to send sensitive data. But please note that it's not enough for the privacy of the traffic, because any man in the middle who listens to the network will see the parameters even though they are inside the body of the request message. So you should encrypt your traffic, always. Now, the server, which provides resources such as HTML files and other content, returns a response message to the client. The response contains completion status information about the request and may also contain requested content in its message body. So every response has a 3-digit response status code, such as 200 OK, 302 found, etc. Now, HTTPS consists of communication over HTTP within a connection encrypted by TLS, Transport Layer Security, or its predecessor, SSL, the Secure Sockets Layer. The main motivation for HTTPS is authentication of the visited website and protection of the privacy and integrity of the exchanged data. So let's see how a typical encrypted connection between the server and the client is established. The client sends the information that the server needs to communicate with the client using SSL. This information contains the client's SSL version number, cipher settings, and session-specific data. The server then sends the information that the client needs to communicate with the server over SSL. The server also sends its own certificate. The client uses the information sent by the server to authenticate the server. So using all data generated in the handshake thus far, the client creates the pre-master secret for the session, encrypts it with the server's public key, and then sends the encrypted pre-master secret to the server. The server uses its private key to decrypt the pre-master secret, and both the client and the server perform a series of steps to generate the master secret. Then, they use the master secret to generate the session keys, which are symmetric keys used to encrypt and decrypt information exchanged during the SSL session and to verify its integrity. The client sends a separate message indicating that the client portion of the handshake is finished, and the server sends a separate message indicating that the server portion of the handshake is finished. So finally, we're going to get into the actual hacking part. I know you're impatient. No, I'm just kidding. I know you're eager, and that's a good thing. So you've got the idea of web and web applications and the interconnectivity and all that, the specifications and how all the standards work and what they actually mean to us. So now it's time to start practicing real hacking in the lab. Now, following a methodology like the OWASP testing guide is really useful. And for the most part in these guides, you will see testing procedures that are divided into different stages, such as reconnaissance, exploitation, and reporting. So here, when I was creating the course, I pretty much did the same and divided the web penetration testing procedures into 7 different stages. And these are mostly acceptable in the field. You can start from where